Welcome to the mechanics of rest. There is no map drawn from the outside. Every measurement ever made of the Milky Way, its diameter, its shape, the position of the sun within it, the number and arrangement of its arms, was made from a point inside it, by instruments sitting inside it, by people who could not step back far enough to see the whole thing at once. That is the problem this episode begins with, and it is a stranger problem than it first appears. To know the size of the room you are standing in, when the room has no walls you can touch and no ceiling you can see, requires a kind of measurement that took centuries to develop and is still being refined. What follows is the chronicle of how that measurement was extended from the Milky Way outward, through the local group, through the superclusters and the vast filaments of the cosmic web, to the edge of what light has had time to cross since the beginning, and then to the question of what lies beyond even that. The numbers grow in ways that resist comprehension, not because they are poorly explained, but because comprehension was simply not built for this scale. The chronicle will move slowly. There is no need to hold any of it. It will carry itself. If this kind of patient science is what you come to Mechanics of Rest for, subscribing keeps it coming. A new journey every week. A like tells the channel that this one was worth the time. The first chapter begins where all measurement of the galaxy began, with a man in a field in England counting stars. Chapter 1. The Shape of the Milky Way. Measuring the Milky Way begins with an admission that the measurement is almost certainly going to be wrong. Not because the instruments are poor or the mathematics faulty, but because the measurer is embedded in the thing being measured, looking outward in all directions from a single fixed point, with no reference outside the system to check against. William Herschel understood this in the 1780s in the way a working scientist understands a problem, not as a philosophical obstacle, but as a constraint to be worked around, and the method he devised to work around it was elegant in its simplicity and limited in ways he could not have anticipated. The method was counting. Herschel reasoned that if stars were distributed roughly uniformly through space, then the number of stars visible in any given direction would be proportional to the depth of the galaxy in that direction. More stars meaning more distance before the edge was reached, fewer stars meaning a shallower column of space. He divided the sky into hundreds of sample regions and counted the stars visible in each through his telescope, producing what he called star gauges. From the resulting numbers, he constructed a model of the Milky Way's three-dimensional shape, a flattened disk, elongated along the plane of the galaxy, with the sun sitting near the center. The disk he derived was roughly 8,000 light-years across and about 1,500 light-years thick, dimensions that were wrong by a factor of roughly 10 in diameter, and wrong in the sun's placement by a factor that would take more than a century to correct. The instrument Herschel used for this work was not the famous 40-foot telescope he built at Slough, though that instrument dominated his later years and became the largest telescope in the world for half a century. The star gauges were conducted with smaller telescopes, more manageable instruments that allowed him to sweep systematically across the sky in a single observing session. The 40-foot telescope, completed in 1789 after years of construction, used a primary mirror 49 inches in diameter cast from speculum metal, a copper tin alloy that required constant repolishing to maintain its reflectivity. The mirror alone weighed nearly a ton. The tube was open at the top, the eyepiece positioned at the upper end so the observer leaned out over the mouth of the tube to look in, and the whole structure was mounted on a rotating frame that Herschel and his assistants moved by hand. Caroline Herschel, his sister and a distinguished astronomer in her own right, worked beside him on many nights as recorder, taking down the star counts and measurements her brother called out in the dark. What the star gauges could not account for was dust. The interstellar medium, the gas and fine particulate matter that fills the space between stars, is not uniformly transparent. In the plane of the galaxy, where the density of both stars and interstellar material is highest, dust absorbs and scatters light significantly, reducing the apparent brightness of distant stars and making remote regions of the disk appear star-poor. Herschel had no way to know this. He assumed the apparent drop-off in stellar density at the edges of his gauged fields indicated the actual edge of the galaxy. In practice, he was seeing the edge of visibility through dust, a boundary imposed not by the galaxy's structure, but by the opacity of the material within it. The galaxy extended far beyond what his counts could reach, and the sun's apparent central position was an artifact of the same obscuration, operating equally in all directions. Dust, in this sense, is the Milky Way's most ordinary component doing its most consequential scientific mischief. It is not rare or exotic. It is the accumulated residue of stellar winds and supernova ejecta, microscopic grains of silicate and carbon compounds drifting through the interstellar medium. In the galactic plane, it reduces the brightness of starlight by roughly 1 to 2 magnitudes per kiloparsec, enough to make a star that would otherwise be visible at 10 kiloparsecs appear as though it sits at 1 or 2. Herschel was mapping not the galaxy's structure, but the galaxy's transparency, and the two turned out to be very different things. Jacobus Kapteyn, a Dutch astronomer working in the early 20th century without access to a large telescope of his own, but with access to photographic plate collections from observatories across the world, refined Herschel's approach using better data and more sophisticated statistical methods. His revised model, developed through the first decade of the 1900s and published in its most complete form in 1906, placed the galaxy's diameter at roughly 30,000 light-years, nearly 4 times Herschel's estimate, with the Sun still near the center. Kapteyn was working with more stars and more careful photometry than Herschel had managed, and his model was correspondingly more detailed. It was still, fundamentally, limited by the same dust problem Herschel had faced. Kapteyn was aware of the possibility of interstellar absorption and attempted to correct for it. His corrections were insufficient, and his Sun remained central for the same reason Herschel's had. The correction came not from better optical telescopes or more careful star counts, but from an entirely different class of object. Globular clusters, dense, roughly spherical assemblies of tens of thousands to several 100,000 stars, gravitationally bound into a compact formation, are visible at distances far greater than individual stars in the disk, partly because they are intrinsically bright, and partly because many of them orbit the galaxy at high latitudes above and below the galactic plane, where dust extinction is much lower. Harlow Shapley, an American astronomer working at the Mount Wilson Observatory in California, recognized in the mid-1910s that the distribution of globular clusters across the sky could provide a map of the galaxy's structure that was far less compromised by dust than any survey of disk stars. Shapley's key tool was the Cepheid period luminosity relation that Henrietta Swan Leavitt had established and Einar Hertzsprung had calibrated. By identifying Cepheid variables within the nearer globular clusters and measuring their periods, Shapley could calculate the distance to those clusters. For clusters too distant for individual Cepheids to be resolved, he developed secondary distance indicators based on the apparent brightness of the cluster's brightest stars, a method that introduced its own uncertainties but extended his reach considerably. By 1918, he had distances to roughly 100 globular clusters and could map their three-dimensional distribution around the galaxy. The distribution he found was not centered on the Sun. The globular clusters formed a roughly spherical halo, and the center of that halo, the gravitational center of the system, lay far from the Sun's position in the direction of the constellation Sagittarius, at a distance Shapley estimated at roughly 50,000 light-years. The Milky Way, he concluded, was vastly larger than either Herschel or Kapton had supposed, with a total diameter of perhaps 300,000 light-years, and the Sun occupied not the center, but a position considerably displaced from it. His estimate overcorrected. The modern value for the distance to the galactic center is approximately 26,000 light-years, and Shapley's calibration of his distance indicators was skewed by factors not yet understood, but the essential finding held. The galaxy was large, the Sun was peripheral, and every previous model had been working at the wrong scale. There is a recurring pattern in the history of cosmic measurement, and Shapley's revision is one of its clearest instances. The answer is almost always larger than the previous answer. Herschel's galaxy gave way to Kapteyn's, which gave way to Shapley's, which gave way to the modern value, each revision expanding the structure being measured while displacing the observer further from any privileged position within it. The pattern is not coincidental. The systematic errors in these measurements, dust extinction, calibration offsets, the difficulty of establishing absolute distances from within the system, all tend to make the measured structure appear smaller and the observer appear more central than is actually the case. Correcting those errors consistently moves in one direction. The modern picture of the Milky Way was assembled from many sources across the second half of the 20th century, and it continues to be refined. The galaxy is a barred spiral, a flattened disk, with a central bar-shaped region from which spiral arms extend, with a total diameter now estimated at approximately 105,700 light-years. The disk itself is not uniform. It is warped at its outer edges, bending slightly above the galactic plane on one side and below it on the other, in a shape that recent surveys with the Gaia Space Telescope have mapped in detail. The Sun sits roughly 26,000 light-years from the center, in a relatively minor feature called the Orion Spur, between the Sagittarius and Perseus arms. At the Sun's distance from the center, the galaxy rotates with a period of approximately 225 to 250 million years, sometimes called a galactic year, meaning the solar system has completed fewer than 20 full orbits since the formation of Earth. The thickness of the disk varies with distance from the center and with which component of the disk is being measured. The thin disk, where most of the galaxy's star formation occurs and where the Sun resides, extends roughly 1,000 light years above and below the midplane. The thick disk, composed of older stars with different chemical compositions and orbital properties, extends to perhaps 3,500 light years. Set against the galaxy's diameter of more than 100,000 light years, these thicknesses give the disk a proportional flatness more extreme than a sheet of paper relative to its width, a structure that is, in its geometry, more like a vast shallow lens than anything a human scale comparison quite captures. The disk's proportional thinness matters because it concentrates interstellar dust in a narrow band along the galactic equator. This concentration is why the optical view through the galactic plane is opaque at most wavelengths of visible light beyond a few thousand light years, not because there is nothing beyond that distance, but because the material in the thin disk absorbs and scatters the light before it can reach an observer on Earth. The galaxy is not hiding its structure, it is simply made of material that, when compressed into a thin disk, acts as its own obscuring medium. The solution to this opacity, the way astronomers eventually read through the dust to map the galaxy's spiral structure, belongs to the next chapter and to the discovery that certain kinds of radiation are not stopped by dust at all. The Sun's position in the Orion Spur, far from the galactic center and between two of the main spiral arms, is neither remarkable nor accidental in any meaningful sense. It is simply where the solar system formed, from a cloud of gas and dust that happened to be at that location in the galaxy roughly 4.6 billion years ago. The galactic center itself is a different environment entirely, a dense, turbulent region of intense star formation, strong magnetic fields, and a supermassive black hole, some 4 million times the mass of the Sun, known as Sagittarius A star, whose presence was inferred from the orbits of stars near the galactic center long before those orbits were traced precisely enough to confirm it. The center is not visible in ordinary light. It is detected in infrared, radio, and X-ray wavelengths that pass through the intervening dust. From its peripheral position in the Orion Spur, the solar system moves through the galaxy at roughly 220 kilometers per second, fast enough to cross the distance from Earth to the Moon in under 2 seconds, and still only a small fraction of the galaxy's rotational speed at other distances from the center. The galaxy does not rotate as a rigid body. Each region orbits independently, with the orbital speed at any given distance determined by the total mass enclosed within that radius. The fact that the rotation speed remains roughly constant even at large distances from the galactic center, rather than declining the way the orbital speed of planets declines with distance from the Sun, is one of the key observations that pointed toward the existence of dark matter. That story belongs to a later chapter as well. What Herschel built in the 1780s, working with a telescope he had largely constructed himself and a method he had devised from first principles, was not an accurate map of the Milky Way. It was the first serious attempt to treat the galaxy as a measurable object, to apply geometry and counting to a structure so large that the measuring instrument was inside it. The map was wrong in its dimensions, wrong in the Sun's position, and limited by a form of opacity he could not see. It was also, in its conception, entirely correct. The galaxy has a shape. That shape can in principle be measured, and the measurement begins with asking what the distribution of stars in different directions actually implies about the structure containing them. Every subsequent model, Kapteyn's, Shapley's, the modern picture assembled from optical surveys, radio maps, and satellite observations, is a revision of that original question, applied with better instruments and a gradually expanding understanding of what the data actually shows. Chapter 2: Measuring the Unmeasurable, the First Cosmic Distance Ladder. Friedrich Bessel spent the better part of 2 years staring at a single star. The star was 61 Cygni, a faint, unremarkable point in the constellation Cygnus, chosen not for any intrinsic interest, but for a specific observational property. It moved. Against the background of more distant stars, 61 Cygni shifted its position across the sky at a rate large enough to suggest it was relatively close to the solar system. Close enough, Bessel calculated, that Earth's annual orbit around the Sun might produce a measurable parallax shift in its apparent position. Parallax is the same phenomenon that makes a nearby object appear to jump against a distant background when you close one eye and then the other. Applied to astronomy, the baseline is not the distance between two eyes, but the diameter of Earth's orbit, roughly 300 million kilometers, and the shift being measured is not inches, but fractions of an arcsecond, divisions of angle so small they had defeated every previous astronomer who had attempted the measurement. The difficulty was not conceptual. The principle of stellar parallax had been understood since antiquity, and astronomers had been attempting to measure it since at least the 17th century. The difficulty was instrumental. To detect the parallax of even the nearest stars requires measuring angular shifts on the order of 1 arcsecond or smaller, 1/3600th of a degree, against a background of stars that are themselves not perfectly stationary. The slightest flexure in a telescope's mounting, the slightest inconsistency in the measurement of angular separation, the slightest atmospheric distortion could overwhelm the signal being sought. Bessel worked at the Königsberg Observatory in what is now Kaliningrad, using a Fraunhofer heliometer, an instrument designed specifically for precise measurement of angular separations between 2 points in the sky, achieved by splitting the telescope's objective lens in half and sliding the 2 halves apart until the image of one star overlaid the image of another. The instrument was exquisitely sensitive and correspondingly demanding to operate. He began his observations of 61 Cygni in 1837 and accumulated measurements across 18 months, correcting carefully for the star's own proper motion, its independent movement through space, which had been the reason he selected it in the first place, and for every instrumental and atmospheric effect he could quantify. When he published his result in 1838, the parallax angle he reported was 0.314 arcseconds, corresponding to a distance of approximately 10.3 light-years. The number has been refined since. The modern value is 11.4 light-years. But the measurement was sound, the method was validated, and for the first time in the history of science, a human being knew how far away a star was. The significance was not merely the number. It was what the number implied about the scale of the problem. If 61 Cygni, one of the nearest stars to the Sun, and selected specifically because its proper motion suggested proximity, lay more than 10 light-years away. Then the vast majority of the stars visible in the night sky lay at distances that parallax measurement, even with the best instruments, could not directly reach. Parallax angles become unmeasurably small at distances beyond a few hundred light-years with ground-based instruments. The Milky Way, even in Herschel's underestimate, stretched tens of thousands of light-years. The gap between what parallax could measure and what the galaxy actually contained was enormous, and bridging that gap required a different kind of distance indicator entirely. The solution arrived not from an observatory equipped with a large telescope, but from a collection of glass photographic plates and the careful attention of a woman whose name took decades to receive the recognition it was owed. Henrietta Swan Leavitt joined the Harvard College Observatory in 1895 as one of a group of women employed to measure and catalog the observatory's photographic plates, a role known at the time as computer, meaning a person who performed computations rather than a machine that did. The observatory's director, Edward Pickering, had assembled this group partly on practical grounds. Women could be hired at lower wages than men, and partly because several of them proved to be exceptional astronomers who made contributions that shaped the field for generations. Leavitt was assigned the task of identifying and characterizing variable stars in the Magellanic Clouds, two irregular satellite galaxies of the Milky Way visible in the southern sky, close enough that all the stars within each cloud could be assumed to lie at roughly the same distance from Earth. This assumption was the key. If all the Cepheid variables in the small Magellanic Cloud were at essentially the same distance, then differences in their apparent brightness reflected differences in their actual luminosity rather than differences in distance. Leavitt measured the brightnesses of thousands of variable stars on dozens of photographic plates, tracking how each star's brightness changed over time and determining its period, the time from one peak brightness to the next. The plates were glass, roughly the size of a large book, each one a photographic record of a region of sky taken through the observatory's telescope during a single exposure. Leavitt would examine each plate under a magnifying glass or low-power microscope, measuring the diameter of each star's image, a larger image indicating a brighter star, and recording the measurement in a logbook. Comparing the same star across plates taken at different times revealed the brightness changes that identified variables. It was slow, precise, repetitive work that required both technical accuracy and the ability to recognize patterns across hundreds of individual measurements accumulated over months. Her 1908 paper noted a striking regularity among the Cepheid variables she had identified in the small Magellanic Cloud. The brighter ones, on average, had longer periods. A star that took 20 days to complete one cycle of brightening and dimming was intrinsically more luminous than one that completed its cycle in 5 days. The relationship was not merely a tendency. It was tight enough, when she had accumulated sufficient data, to be described as a precise mathematical function. Her 1912 paper documented 25 Cepheid variables in the small Magellanic Cloud, with periods ranging from 1.25 to 128 days, and demonstrated the period-luminosity relationship with sufficient clarity to make its implications plain. If the absolute luminosity of even a single Cepheid could be determined by an independent method, the relation could be used to calculate the luminosity, and from the luminosity and the apparent brightness, the distance of any Cepheid anywhere in the observable sky. Leavitt understood what the relationship meant. She noted it plainly in the 1912 paper in the measured language of scientific reporting that the relation, once calibrated, would provide a means of measuring distances to objects far beyond the reach of parallax. She did not have the data required to perform that calibration herself. It required a Cepheid close enough for parallax to work, and none were close enough for the instruments then available. The calibration fell to Einar Hertzsprung, a Danish astronomer who in 1913 used statistical methods applied to the proper motions of nearby Cepheids, a technique that could extract approximate distances from the way a group of stars moved across the sky, even when individual parallaxes were too small to measure, to establish the absolute luminosity scale. His calibration was uncertain by perhaps 50%, and subsequent refinements would shift the numbers, but the latter had its first rung anchored. What the period luminosity relation had done, in practical terms, was extend the reach of distance measurement from a few hundred light-years to several million. A Cepheid bright enough to be identified and have its period measured could be used as a distance indicator, regardless of what else was visible in its vicinity. The tool did not require a nearby reference star, did not require the object to have a measurable proper motion, did not require anything except a clear light curve and a period that could be timed. It was, in the vocabulary of the field, a standard candle, an object whose intrinsic brightness was known, allowing distance to be inferred from apparent brightness, in the same way that the distance to a lamp can be estimated if you know how bright the lamp actually is. The distance ladder's architecture, the structure that makes it a ladder rather than a single measurement, is worth sitting with for a moment, because it shapes everything that follows in the history of cosmic distance measurement. Each rung depends on the rung below it. Parallax provides distances to nearby stars. Those distances calibrate the luminosities of Cepheid variables. The Cepheid luminosities provide distances to nearby galaxies. Those galaxy distances calibrate other, brighter standard candles that can be seen at greater distances still. An error at any level propagates upward through every subsequent measurement, amplified at each rung. When the calibration of Cepheid luminosities was revised, and it was revised multiple times across the 20th century, as calibration methods improved, every distance derived from Cepheid measurements shifted accordingly, and every distance derived from those distances shifted with them. The history of cosmic distance measurement is substantially a history of calibration revisions, each one moving the numbers and requiring the reconstruction of conclusions built on the previous calibration. This dependency is not a weakness of the method so much as a structural feature of the problem. There is no way to measure a distance of 1,000,000 light-years directly. The measurement is always a chain of inferences, each link dependent on the last, extending outward from the handful of nearby stars whose distances can be established by geometry alone. The chain is as strong as its weakest link and as long as the most distant standard candle that can be reliably identified. Leavitt's contribution was to forge the link that made the chain long enough to reach beyond the Milky Way. and to do so from the quiet, sustained attention applied to several hundred photographic plates in a Cambridge observatory without access to a telescope of her own. Hertzsprung recognized the significance of what Leavitt had found quickly. His 1913 calibration paper cited her work directly and applied the result with the urgency of someone who understood that a tool of this power should be put to use immediately. The calibration he produced placed the small Magellanic Cloud at a distance of roughly 30,000 light-years, a significant underestimate of the modern value of about 200,000 light-years, attributable largely to the same interstellar dust problem that had plagued Herschel and Kapteyn, and to the imprecision of the statistical parallax method he used. But the order of magnitude was in the right range, the method was sound, and other astronomers working in the following decade would apply the tool to targets that Leavitt and Hertzsprung had not yet reached. The calibration problems were real and consequential, and they accumulated in a specific direction. Interstellar dust dims the light of Cepheids just as it dims the light of ordinary stars, making them appear fainter and therefore more distant than they actually are. Before the existence and systematic effects of interstellar dust were properly understood and quantified, Cepheid-based distances tended to be overestimates. Additionally, it would eventually emerge that there are two distinct populations of Cepheid variables with different period luminosity relations, a distinction not recognized until the 1950s when Walter Bade, using the new 200-inch telescope at Palomar, found that the calibration used for Cepheids in the Milky Way did not apply to a different class of Cepheid found in globular clusters. Correcting for this doubled the estimated distances to all galaxies measured with the older calibration overnight. Each correction made the universe larger, the pattern that Shapley's revision had established at the scale of the Milky Way, each new measurement revealing a structure more extensive than the previous measurement had implied, held at every larger scale as the distance ladder was extended. The universe, as measured by the tools available at any given moment, was always in the process of being found to be bigger than previously thought. And the primary reason was always the same: a systematic error in the distance measurement that made things appear closer than they were. By the mid-1920s, the period luminosity relation had been calibrated well enough, uncertainly but well enough, that an astronomer with access to a large enough telescope could, in principle, identify a Cepheid variable in a distant nebula, measure its period over a series of nights, and calculate from that period and the calibrated relation a distance to the nebula. The question of whether that distance, once calculated, would place the nebula inside the Milky Way or far beyond it had been debated formally and publicly for years. The measurement that settled it required the largest telescope in the world and a photographic plate on which a single variable star in a sea of tens of thousands changed its brightness on a schedule that matched the period luminosity relation precisely. That measurement was made in 1923, and it belongs to the next chapter. Chapter 3: The Spiral and Its Arms. The Milky Way was known to be a spiral before anyone could see its spiral structure. This sounds like a paradox, but is simply the result of two kinds of evidence arriving in a specific order. The morphological evidence came first, from observations of other galaxies whose structure was visible because they lay outside the obscuring material of the galactic plane. And the structural evidence for our own galaxy came later, from instruments capable of reading through the dust that made direct optical mapping impossible. By the late 1940s, astronomers were confident the Milky Way was a spiral, on the grounds that most large disk galaxies appeared to be spirals, and the Milky Way's mass, rotation, and general properties matched the class well, confirming that confidence required solving the dust problem, and solving the dust problem required abandoning visible light entirely. The optical approach came first, and it came from a recognition that certain stars, the most luminous, most massive, shortest-lived members of the stellar population, were reliable tracers of spiral structure in other galaxies. In external spirals, the bright bluish-white stars of spectral type O and B, together with the glowing clouds of ionized hydrogen associated with regions of active star formation, were consistently found in the spiral arms rather than between them. OB associations, as these groupings were called, were not uniformly scattered through a galaxy's disk. They were concentrated in arc-shaped features that defined the arm's positions. William Morgan, an astronomer at Yerkes Observatory in Wisconsin, reasoned that the same tracers should work in the Milky Way if their distances could be measured accurately enough to reveal the arc-shaped distribution. Morgan worked with Stuart Sharpless and Donald Osterbrock through the early 1950s, compiling spectroscopic observations of OB stars and HII regions, the ionized hydrogen clouds that accompany massive star formation within a few thousand light-years of the Sun. Spectroscopic parallax, a method that used the detailed properties of a star's spectrum to estimate its intrinsic luminosity and thus its distance, provided the distance measurements. By 1951, they had accumulated enough data points to detect 3 arc-shaped features in the distribution of their sample, segments of what appeared to be spiral arms curving through the region of the galaxy, accessible to optical observation. Morgan presented the result at the December 1951 meeting of the American Astronomical Society, displaying a map that showed, for the first time, segments of the Milky Way's spiral structure traced from stellar positions. The arms they identified correspond to portions of what are now called the Sagittarius arm, the Orion spur where the Sun resides, and the Perseus arm. The optical map was real and significant, and it was also limited to a small volume around the Sun. Dust prevented optical methods from reaching more than a few thousand light-years into the galactic plane, which meant the full spiral pattern, the arms extending tens of thousands of light-years from the galactic center and wrapping around it multiple times, remained inaccessible to any instrument that depended on visible light. The solution had been identified theoretically 7 years before Morgan's optical mapping by a Dutch astronomer working under German occupation during the Second World War. Hendrik van de Hulst was a graduate student in Utrecht in 1944 when he was asked by his supervisor, Jan Oort, to investigate whether neutral hydrogen, the most abundant element in the interstellar medium present in vast clouds throughout the galactic disk, might emit radiation at a wavelength that radio telescopes could detect. Quantum mechanics predicted that the hydrogen atom in its ground state could exist in 2 slightly different configurations, depending on the relative orientation of the electron's spin and the proton's spin. When a hydrogen atom transitions spontaneously from the higher energy configuration to the lower one, it would emit a photon at a very specific wavelength, 21.106 centimeters, corresponding to a frequency of 1420.4 megahertz. The transition was extremely rare for any individual atom. An average hydrogen atom in space waits roughly 11 million years before making it spontaneously. But the interstellar medium contains so many hydrogen atoms that the aggregate emission would be detectable. More importantly, radio waves at 21 centimeters pass through interstellar dust without significant absorption. A radio telescope sensitive to this frequency could, in principle, map the distribution of neutral hydrogen across the entire galactic disk, dust or no dust. Van der Hulst published his prediction in 1944 in a Dutch journal during the occupation, and it circulated among astronomers who understood its implications immediately. After the war, groups in the Netherlands, Australia, and the United States began independently working toward detection of the 21 centimeter line. The Americans reached it first, though by a margin smaller than they anticipated. Harold Ewan was a graduate student in physics at Harvard, working under Edward Purcell, who would share the 1952 Nobel Prize in Physics for his earlier work on nuclear magnetic resonance, and together they designed and built a small horn antenna on the roof of Harvard's Lyman Laboratory, constructed largely from materials available in the physics department's supply rooms. The antenna was not an imposing instrument. It was a rectangular metal horn, open at one end to receive radio waves from the sky, connected to a receiver that could be tuned to frequencies near 1420 megahertz. It cost a fraction of what a conventional optical telescope would have required and occupied a corner of a laboratory rooftop. On March 25, 1951, Ewan and Purcell detected the 21 centimeter emission line from neutral hydrogen in the Milky Way. The signal appeared as a peak in the radio spectrum at the predicted frequency, Doppler shifted slightly by the motion of the hydrogen clouds relative to the Earth, a shift that would prove to be not merely a complication, but a tool, since the Doppler shift in the line's frequency revealed the velocity of each cloud along the line of sight, allowing astronomers to separate overlapping clouds at different distances by their different velocities. Before submitting their result for publication, Ewan and Purcell contacted the Dutch group, Van der Hulst's colleagues at Leiden, who had been working toward the same detection, and shared their findings, allowing the two groups to publish simultaneously. An Australian group detected the line independently within weeks. The coordination reflected a collegial awareness that multiple groups had invested years in pursuing the same goal, and that the scientific community's interest was better served by simultaneous recognition than by a priority race. The Doppler mapping that followed over the next decade transformed the picture of galactic structure. As a radio telescope swept across the galactic plane, the 21 centimeter emission arrived from hydrogen clouds at many different distances, each cloud moving at a slightly different velocity due to the galaxy's differential rotation. By measuring how the frequency of the emission line varied with direction, and combining those frequency measurements with a model of galactic rotation, radio astronomers could reconstruct the three-dimensional distribution of hydrogen throughout the disk. The maps that emerged from Dutch, Australian, and American radio observatories through the 1950s revealed the Milky Way's spiral structure on a scale that optical methods could not approach. Arms of dense hydrogen extending from the galactic center outward, curving through the disk in the characteristic pattern of a barred spiral galaxy. Understanding why the arms existed as distinct features, why the hydrogen and stars were concentrated in them rather than smoothly distributed through the disk, required a conceptual step that had been taken independently by Bertil Lindblad in Sweden through the 1920s. Lindblad had developed a theoretical framework for the rotation of disk galaxies that included the idea of differential rotation, that different parts of a galaxy's disk orbit the center at different rates, with inner regions completing orbits more quickly than outer ones. This differential rotation had an immediate geometrical consequence for any initially straight feature in the disk. It would be wound progressively tighter over time, the inner end of any radial feature pulling ahead of the outer end with each orbit. Any pattern of enhanced density that formed as a radial feature would be sheared by differential rotation into a trailing arc, naturally producing the swept-back appearance of spiral arms. Jan Oort, working in the Netherlands, confirmed differential galactic rotation observationally in 1927, demonstrating from the systematic patterns in stellar velocities that the Milky Way's disk rotated differentially in a way consistent with Lindblad's theoretical framework. Oort also used the velocity patterns to determine the direction of the galactic center, confirming Shapley's identification of the Sagittarius direction, and to estimate the distance from the Sun to the center, arriving at a value that has been refined but not drastically revised in the centuries since. The spiral arms themselves, however, presented a difficulty that differential rotation made sharper rather than softer. If the arms were simply regions of higher stellar density rotating with the disk, differential rotation would wind them tighter with each orbit until, after a few galactic years, they would be wrapped so many times around the center that they would no longer appear as distinct features. The Sun has completed perhaps 18 to 20 orbits of the galaxy since its formation, which would be more than enough winding to erase any primordial arm structure. The arms persist, which means they cannot be fixed collections of material rotating together. The resolution, developed in the 1960s by the theoretical work of C.C. Lin and Frank Hsu at MIT, was that spiral arms are density waves rather than material structures, patterns of compression that move through the disk at a different angular velocity than the stars and gas themselves. The arms are regions where the disk material is temporarily more compressed, moving through them the way a traffic slowdown moves backward through a highway, even as the individual cars move forward. Stars and gas clouds enter the arms, spend time in the compressed region, and emerge from the other side. The arm as a pattern persists. The stars within it at any given moment are not the same stars that were there 100 million years ago. New star formation is triggered by the compression in the arms. The dense gas clouds that enter the arms are squeezed enough to collapse into new stars, which is why the most luminous and shortest-lived stars, the OB associations that Morgan used as tracers, are found preferentially in the arms. They form there, burn brilliantly for a few million years, and die before they have moved far from their birthplace. The Milky Way's full spiral architecture, assembled from radio surveys, infrared observations, and more recent data from the Gaia Space Telescope's precise stellar position measurements, consists of four major arms: the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm, together with several shorter arm segments and spurs. The Sun sits in one of these shorter features, the Orion spur, also called the local arm, lying between the Sagittarius and Perseus arms at a galactic radius of about 26,000 light-years from the center. The spur is not a major arm in the same class as the four primary features, but is itself a substantial structure, several thousand light-years long, the region of the galaxy within which the solar system has spent its entire existence. At the galaxy's center, the spiral arms do not extend all the way in. Instead, the disk transitions into a bar, an elongated, roughly elliptical concentration of stars oriented at an angle to the line connecting the Sun to the galactic center, stretching perhaps 27,000 light-years from end to end. The bar rotates as a unit, unlike the differentially rotating disk around it, and its ends are the points from which the major spiral arms originate. Barred spirals are common among disk galaxies. Perhaps 2/3 of all spiral galaxies show some degree of bar structure, and the Milky Way's bar was suspected for decades before infrared surveys penetrating the galactic dust confirmed its presence and dimensions. The full rotation of the galaxy at the Sun's radius, one galactic year of 50 million years, provides a useful reference for the timescales involved in galactic structure. The last time the solar system was at its current position in its orbit, the most recent mass extinction had just concluded, and the dinosaurs were a relatively recent development. 2 galactic years ago, complex multicellular life had not yet appeared on Earth. The arms have wound and rewound many times over in that span, the density wave pattern shifting slowly while the disk material rotated through it, star formation proceeding continuously in the compressed regions where gas clouds entered the arm and were squeezed into collapse. The galaxy's structure is not ancient and fixed, but ongoing, a slow, continuous dynamic process that has been operating since the disk formed and will continue operating long after any present feature has been entirely reshaped. What the 21-centimeter line made possible was not just a map, but a method, a way of reading through the opaque material of the galactic plane to the hydrogen distributed throughout the disk, converting frequency shifts into velocities, velocities into distances, and distances into a three-dimensional picture of the galaxy's structure. The signal Van de Hulst predicted in wartime Utrecht, detected by Ewan and Purcell on a Cambridge rooftop in the spring of 1951, travels through the dust of the galactic plane without any more interaction than a slight dispersion at much longer wavelengths. It arrives at the antenna carrying information about the cloud that emitted it, its velocity, its temperature, its density, information that visible light from the same cloud, had any been detectable, could not have carried through the intervening material. The radio sky and the optical sky are different skies, and the Milky Way that radio astronomy revealed was a larger, more structured, more dynamic place than the one optical astronomy had been able to describe. Chapter 4: The Local Group. Beyond the Milky Way, The question was not what lay there, but whether anything lay there in the sense that mattered. Whether the faint, diffuse objects catalogued in increasing numbers through the 18th and 19th centuries were part of the galaxy or entirely separate from it. Island universes in their own right, at distances that dwarfed anything yet measured. The question had been formally unresolved for decades by the time it was settled, and its settlement came not from a new theory or a new argument, but from a single measurement made on a single photographic plate on a single night in October 1923. Everything that follows in the history of extragalactic astronomy, the local group, the superclusters, the observable universe, the expansion, traces back to that plate and the number written on it in red pencil. The objects at the center of the controversy were the spiral nebulae, faint extended patches of light, many displaying a pinwheel structure visible in long exposure photographs, catalogued by the thousands in systematic surveys of the sky. Charles Messier had listed the brightest of them in the late 18th century, more interested in avoiding them than studying them. His catalog was a guide for comet hunters, marking objects that could be mistaken for comets. John Dreyer's New General Catalog, published in 1888, listed nearly 8,000 nebulae and star clusters. Their nature was genuinely uncertain. Some were clearly clouds of gas within the Milky Way, the Orion Nebula, the Crab Nebula, objects visibly connected to the surrounding stellar population. Others, the spiral nebulae in particular, resisted easy classification. Vesto Slifer, an astronomer at the Lowell Observatory in Arizona, began measuring the spectra of spiral nebulae in 1912, motivated initially by the question of whether they were solar systems in formation, a hypothesis then current that the spiral structure reflected a rotating disk of gas collapsing into a new planetary system. His spectrograph required exposure times of 20 to 40 hours per nebula, spread across multiple nights, to accumulate enough light from these faint objects for a usable spectrum. The spectra he obtained contained absorption lines, the same dark lines produced by specific chemical elements absorbing light at characteristic wavelengths, but the lines were shifted from their laboratory positions. Most of the nebulae showed redshifts. Their lines were displaced toward longer wavelengths, indicating recession velocities of hundreds, or in some cases thousands of kilometers per second. A few, including the Andromeda Nebula and its neighbors, showed blue shifts, indicating approach. By 1917, Slipher had measured velocities for 25 spiral nebulae, and the predominantly large recession velocities were difficult to explain if the objects were clouds within the Milky Way. The galaxy's escape velocity was far too low to retain objects moving at such speeds, but without distance measurements, the velocities alone could not settle the question of what the nebulae actually were. The Great Debate of April 1920, organized by the National Academy of Sciences in Washington and set formally as an exchange between Harlow Shapley and Heber Curtis, brought the competing positions into direct confrontation. Shapley argued that the spiral nebulae were relatively nearby gas clouds within or close to the Milky Way, which he believed to be an enormous galaxy, his 300,000 light-year estimate, encompassing the Magellanic Clouds and possibly other nearby objects. Curtis argued that the Milky Way was much smaller, closer to Kapteyn's estimate, and that the spiral nebulae were external galaxies, island universes comparable to the Milky Way in size, separated from it by vast distances. Each side had evidence. Each piece of evidence had problems. Shapley cited what appeared to be novae observed in spiral nebulae at luminosities that, if the nebulae were external galaxies, would have made them implausibly bright, brighter than entire galaxies. Curtis cited the large recession velocities Slipher had measured, the absence of spiral nebulae near the plane of the Milky Way, suggesting they were a different class of object avoiding that region, and the structural similarity of the spirals to what an external view of the Milky Way might look like. Neither argument was decisive. The debate ended without resolution, and with neither participant particularly persuaded by the other, which is how most debates about genuinely open scientific questions tend to end. Edwin Hubble had been working at the Mount Wilson Observatory since 1919, using the 100-inch Hooker telescope, at the time the largest operational telescope in the world, with a primary mirror 254 centimeters across. Situated on a mountain above Los Angeles, where the seeing conditions were reliably good and the light pollution of the city below had not yet grown to its present level. Hubble was systematic, meticulous, and ambitious, and he had been photographing the Andromeda Nebula and other nearby spirals with the Hooker telescope, accumulating plates of sufficient depth and resolution to resolve individual stars in the outer regions of the nearest objects. On the night of October 5 to 6, 1923, examining a plate of the Andromeda Nebula taken the previous night, Hubble identified what he initially took to be 3 novae, stars undergoing sudden brightening events that made them temporarily visible at great distances. He marked them with the letter N on the plate. Comparing this plate with earlier plates of the same region, he found that one of the 3 objects he had marked was not a nova. Its brightness varied in a regular, periodic way across multiple plates spanning several weeks, brightening and dimming on a schedule that matched the behavior of a Cepheid variable. Hubble crossed out the N he had written on the plate and replaced it with VAR, the exclamation mark, an unusual intrusion into the controlled vocabulary of observational notation. He measured the Cepheids period, about 31 days, and applied the Leavitt-Hertzsprung period luminosity relation to calculate its distance. The result was approximately 900,000 light-years, using the calibration available to him at the time. Even accounting for the uncertainties in the calibration, the number placed the Andromeda Nebula far beyond any possible boundary of the Milky Way. The modern value, refined through decades of improved calibration, is 2.537 million light-years. Hubble wrote to Shapley with the result. Shapley, who had championed the large Milky Way and the nearby spiral nebulae position, read the letter and reportedly said to a colleague that it was the letter that had destroyed his universe. The comment is probably apocryphal in its exact phrasing, but accurate in its substance. Hubble's measurement did not merely extend the known universe, but restructured it, replacing the Milky Way as the dominant feature of cosmic geography, with a universe in which the Milky Way was one galaxy among many, its nearest neighbor alone more than 2 million light-years away. The Andromeda Galaxy. The Andromeda Nebula's proper name, once its nature was established, is not merely the nearest large galaxy to the Milky Way, but in several respects its near twin. It is a spiral galaxy, somewhat larger than the Milky Way by most estimates, containing perhaps 1 trillion stars distributed through a disk roughly 220,000 light-years in diameter. It has its own system of satellite galaxies, its own globular cluster population, its own central bar structure and spiral arms. Seen from a distance, it would resemble the Milky Way closely enough that the two could be confused, distinguished mainly by the details of their bar structure and the exact arrangement of their arms. The two galaxies are gravitationally bound to each other. Slipher's blue shift measurement of Andromeda reflected this, the galaxy approaching at approximately 110 kilometers per second along the line of sight, and their eventual merger, predicted to occur in roughly 4.5 billion years, will produce a single large elliptical galaxy that astronomers studying the question have taken to calling Milkomeda. The light arriving from Andromeda right now left the galaxy approximately 2.537 million years ago. At that time, the genus Homo had not yet appeared in the fossil record. The hominid lineage was producing Australopithecus and early Paranthropus, bipedal but with brain volumes not much larger than a chimpanzee's. The photons now entering telescopes and cameras pointed at Andromeda began their journey before stone tools had been invented, traveled through the intergalactic void for the entirety of human prehistory and history, and arrived having experienced nothing in transit, no scattering, no absorption, no interaction with any material. They carry information about the state of Andromeda's stellar population 2.537 million years in the past, which is the only kind of information about Andromeda that can ever be available to any observer in the Milky Way. The present state of Andromeda, whatever it may be, will not be visible from here for another 2.537 million years. The Milky Way and Andromeda are the two dominant members of a larger gravitationally bound system called the Local Group, a collection of galaxies sharing a common gravitational fate, moving together through the universe as a unit even as each member orbits the system's center of mass. The Local Group contains approximately 54 confirmed member galaxies, though the census is incomplete. Small, faint dwarf galaxies at the group's periphery are difficult to detect, and new members are still being identified by surveys capable of resolving their low surface brightness. The group's diameter is roughly 10 million light-years, a scale that dwarfs the Milky Way by a factor of nearly 100. The members of the Local Group range enormously in size and luminosity. The Milky Way and Andromeda are by far the largest, each accompanied by retinues of smaller satellites. The Milky Way's satellites include the Large Magellanic Cloud, a dwarf irregular galaxy approximately 160,000 light-years away, containing roughly 30 billion stars, and the Small Magellanic Cloud at about 200,000 light-years. The same objects leave it studied for her period luminosity work. The Sagittarius dwarf galaxy, discovered in 1994, is so close, roughly 70,000 light-years from the galactic center, and so diffuse that it was not recognized as a separate galaxy until late in the 20th century. It is currently being tidally disrupted by the Milky Way's gravity, its stars stretched into a long stream that wraps around the galaxy multiple times. Andromeda has its own complement of satellites, including M32 and M110, visible as small companions in long exposure images. And the Triangulum galaxy, Messier 33, lies nearby as a third, smaller spiral member of the local group. Beyond the confirmed satellites and companions, the local group contains numerous dwarf spheroidal galaxies, faint, roughly spherical systems containing relatively few stars, little gas, and little ongoing star formation. Objects like the Sculptor Dwarf, the Fornax Dwarf, and the Carina Dwarf lie at distances of a few 100,000 light-years from the Milky Way, gravitationally bound to it, moving through the galactic halo in elongated orbits. Their existence and properties, particularly their internal velocity dispersions, which imply far more mass than their visible stars account for, are among the observations that most directly constrain models of dark matter on the scale of individual galaxy halos. The local group is itself not isolated. It sits at the periphery of a much larger concentration of galaxies centered on the Virgo cluster, roughly 54 million light-years away, a vast assemblage of more than 1,000 galaxies whose combined gravity exerts a detectable pull on the local group, slightly retarding its expansion away from the cluster's center. This larger structure, of which the local group is a small and outlying member, is the next threshold of scale that the Chronicle must cross. And it is a threshold that took much of the 20th century to map with any precision. The tools for crossing it were built partly from what Hubble had found in 1923 and partly from what Slipher's velocity measurements implied, that the galaxies were not merely present at these distances, but moving, and moving in a pattern that would turn out to carry information about the entire history and geometry of the universe. Chapter 5: Standard Candles and the Expanding Sky. Hubble had velocities from Slipher and distances from Cepheids, and by 1929 he had enough of both to see a pattern. Plotting the recession velocities of nearby galaxies against their distances produced a relationship that was linear or close enough to linear given the measurement uncertainties. Galaxies twice as far away were receding roughly twice as fast. Galaxies 3 times as far away roughly 3 times as fast. The relationship held across the range of distances Hubble could measure with confidence, which at that point extended to perhaps 6 or 7 million light-years, not far by the standards of what would come later, but far enough that the pattern was unmistakable. He published it in 1929 in a paper that ran to fewer than 4 pages, presenting the data with characteristic economy and drawing the conclusion that distance and recession velocity were proportional, related by a constant that has since carried his name. The constant he derived was approximately 500 kilometers per second per megaparsec, meaning that for every megaparsec of distance, roughly 3.26 million light-years, a galaxy's recession velocity increased by about 500 kilometers per second. The modern accepted value is somewhere between 67 and 73 kilometers per second per megaparsec, depending on the measurement method, a discrepancy that will require revisiting. The enormous difference between Hubble's 1929 value and the modern one is not a sign that his observation was wrong, but that his distances were wrong. The Cepheid calibration he was using, before Bade's 1952 revision distinguishing 2 populations of Cepheid variables, placed galaxies at distances roughly half what they actually were, compressing the distance scale and inflating the derived constant accordingly. The proportionality he identified was correct. The scale was off. 2 years before Hubble's paper, a Belgian priest and physicist named Georges Lemaire had derived the same relationship from a different direction entirely. Lemaire was working not from observational data, but from Einstein's field equations of general relativity, which admitted solutions describing a universe that was not static, but expanding, a possibility Einstein himself had resisted, introducing a cosmological constant into his equations, specifically to produce a static solution, a decision he would later describe as his greatest blunder. Lemaitre found in 1927 that an expanding universe would naturally produce a proportional relationship between distance and recession velocity, derived the constant from the available observational data, Slipher's velocities, and Hubble's distance estimates, and published the result in a Belgian scientific journal in French. The paper was not widely read. When it was translated into English in 1931, the editors omitted the section in which Lemaire derived the constant from observational data, a suppression whose precise circumstances have been debated by historians of science since. Hubble, working purely empirically, reached the same conclusion independently and published it in a venue that the astronomical community was reading. The relationship is called Hubble's law in most contexts, though a growing number of scientific bodies have moved toward calling it the Hubble-Lemaitre law in acknowledgement of the prior derivation. What the relationship meant physically was not immediately obvious from the data alone. A universe in which more distant galaxies recede faster is consistent with an explosion centered on our location, which would restore the Milky Way to a privileged central position. But it is equally consistent with a uniformly expanding space in which every point recedes from every other point at a rate proportional to the distance between them. The second interpretation, supported by the theoretical framework Lemaitre and independently Alexander Friedmann had developed from general relativity, implies that the universe has no center, or rather that every point in it is equally a center, that the recession of distant galaxies is not motion through space, but the expansion of space itself. Running the expansion backward in time leads to a state of increasing density and temperature at earlier and earlier moments, converging on what Lemaitre called the hypothesis of the primeval atom and what later became known, initially as a term of mockery from Fred Hoyle, as the Big Bang. Extending the distance ladder beyond the reach of Cepheid variables required new standard candles, objects brighter than individual Cepheids that could be identified and calibrated at greater distances. The development of these candles occupied much of 20th century observational cosmology. Brent Tully and J. Richard Fisher published a relation in 1977 connecting the rotational velocity of a spiral galaxy, measurable from the width of its 21-centimeter emission line, to its intrinsic luminosity. A faster rotating galaxy is more massive and more luminous, and the relationship between rotation speed and luminosity is tight enough to serve as a distance indicator. Measure the rotation, infer the luminosity, compare to the apparent brightness, calculate the distance. The Tully-Fisher relation extended the distance ladder to tens of millions of light years, far beyond what Cepheids could reach even with the largest optical telescopes then available. Wendy Friedman led the Hubble Space Telescope Key project through the 1990s, a systematic program designed to resolve the long-standing uncertainty about the Hubble constant by measuring Cepheid distances to a carefully selected sample of galaxies at distances up to about 25 megaparsecs. The HST's resolution, operating above the blurring effects of Earth's atmosphere, allowed Cepheid variables to be identified in galaxies far too distant for ground-based telescopes to resolve individual stars reliably. The Key project's final result, published in 2001, gave a Hubble constant of 72 plus or minus 8 kilometers per second per megaparsec, a value with an uncertainty small enough to distinguish between the competing cosmological models then under consideration, and a value consistent with a universe roughly 13 to 14 billion years old. But Cepheids in the Tully-Fisher relation, however refined, could not reach the distances required to measure the large-scale behavior of the universe's expansion. The question of whether the expansion was slowing under gravity, as most cosmologists expected, or doing something else. For that, a brighter standard candle was needed, one visible across billions of light years. Type 1a supernovae provided it. These events occur in binary star systems containing a white dwarf, the dense remnant of a dead star, typically about the mass of the Sun compressed into a volume roughly the size of Earth, that is accreting material from a companion star. When the white dwarf accumulates enough mass to exceed a critical threshold, approximately 1.4 times the mass of the Sun, it undergoes a thermonuclear explosion that destroys it entirely. Because the trigger point is always the same mass, the explosion is always approximately the same energy, producing a peak luminosity of roughly 5 billion times the luminosity of the Sun. A Type 1a supernova at peak brightness outshines its entire host galaxy and can be detected at distances of billions of light years with sufficient telescope aperture. The peak luminosity is not perfectly uniform. It varies by perhaps 30% from event to event, but a refinement discovered in the 1990s by Mark Phillips made the candle far more precise. Phillips found that brighter Type 1a supernovae declined more slowly from peak than fainter ones. A relationship between peak luminosity and the rate of brightness decline that allowed the intrinsic luminosity of any individual event to be determined from its light curve alone, correcting the 30% variation down to a few percent. With this correction applied, Type 1a supernovae became the most precise distance indicators available at cosmological distances. Two independent teams applied this tool to the question of cosmic expansion in the late 1990s. The High Z Supernova Search Team, led by Brian Schmidt and including Adam Rees as the lead analyst, and the Supernova Cosmology Project, led by Saul Perlmutter, were searching for Type 1a supernovae at high redshifts, meaning large distances, and comparing their apparent brightnesses to what a uniformly expanding or decelerating universe would predict. Both teams expected to find that the supernovae were somewhat brighter than a freely coasting universe would produce, indicating that gravity had been slowing the expansion and the universe was denser in the past. The data showed the opposite. The high redshift supernovae were dimmer than expected, not brighter, meaning they were farther away than a coasting universe would place them, meaning the expansion had been slower in the past and was faster now. The universe's expansion was not decelerating, it was accelerating. The result was unwelcome in the sense that no one had predicted it, and no existing theoretical framework comfortably accommodated it. Both teams checked and rechecked their analysis, looking for systematic errors, dust obscuring the supernovae and making them appear dimmer, selection effects in how the supernovae were found, errors in the light curve correction. The checks held. Approximately 50 Type 1a supernovae at redshifts between 0.3 and 1 contributed to the combined dataset, enough to make the statistical case robust. When the two teams compared results and found they agreed, the conclusion became difficult to avoid. Something was causing the expansion of the universe to accelerate, working against gravity on cosmological scales, and that something had no established identity. It was given the name dark energy, a placeholder acknowledging that its nature was entirely unknown and attributed mathematically to a term in Einstein's field equations that Einstein had introduced and abandoned. The cosmological constant, now revived not as an ad hoc correction, but as a measured quantity with a specific value. The 2011 Nobel Prize in Physics went to Schmidt, Rees, and Perlmutter for this discovery, with the citation noting that the finding had fundamentally changed the understanding of the universe. Dark energy, on current estimates, comprises approximately 68% of the universe's total energy content. The dominant component, more than all matter combined, driving the accelerating expansion that will eventually push all galaxies beyond the local group, so far away that their light can no longer reach us, leaving the local group in a universe that appears, to any future observer, to contain only itself. The Hubble constant remains a source of active contention in cosmology, for a reason that the supernova discovery made sharper rather than softer. Two classes of measurement give systematically different values. Early universe measurements. Those based on the cosmic microwave background, the relic radiation from the first 380,000 years, analyzed by the Planck satellite, give a value of approximately 67.4 kilometers per second per megaparsec. Late universe measurements, those based on Cepheids, Type 1a supernovae, and other distance ladder methods in the nearby universe, give values clustering around 73 kilometers per second per megaparsec. The discrepancy is roughly 9%, which sounds small but is many times larger than the stated measurement uncertainties of either method. If both measurements are correct and their error estimates are accurate, the discrepancy implies that something in the standard cosmological model is incomplete. New physics operating either in the early universe, the late universe, or both. This tension, called the Hubble tension, is currently one of the most actively discussed problems in observational cosmology, and it has not been resolved. Friedman's more recent work, using a different calibration path for the distance ladder that relies on stars called the tip of the red giant branch rather than Cepheids, has produced values intermediate between the two camps, around 69 to 70 kilometers per second per megaparsec, suggesting that at least part of the tension may reflect systematic errors in the Cepheid calibration rather than new physics. The debate continues, with new measurements from the James Webb Space Telescope beginning to clarify the Cepheid calibrations at the level of detail required to test whether the tension is systematic or real. Whether the resolution will require adjusting one of the measurement chains or revising the underlying cosmological model remains genuinely open. What the distance ladder built from Leavitt's period luminosity relation, extended through the Tully-Fisher relation, and the supernova standard candle, established is not just a set of numbers, but a framework within which those numbers have meaning. The recession velocities Slipher measured in 1912 to 1917 were velocities in a universe whose geometry was not yet understood. They became evidence for an expanding universe only when distances were added to the picture. The acceleration discovered in 1998 was invisible in the velocity data alone and emerged only when distances precise enough to detect the few percent deviation from a coasting universe were achievable. Every additional rung of the distance ladder added not merely reach but resolving power, the ability to distinguish between models of the universe that agreed at shorter distances and diverged at longer ones. The universe's large-scale behavior is, in this sense, written in the relationship between distance and velocity, and reading that relationship has required a century of increasingly precise measurement with increasingly refined tools. Each generation of astronomers building on the calibrations left by the last. Chapter 6: Superclusters and the Cosmic Web. If galaxies cluster, the next question follows naturally. Do the clusters themselves cluster? The answer, arrived at gradually through the second half of the 20th century, was yes. And the structure that clustering produces at successively larger scales is not a simple hierarchy of ever larger clumps, but something geometrically distinct, a pattern that no one anticipated and that required both new observational tools and new ways of representing three-dimensional data to see clearly. The universe at the scale of hundreds of millions of light-years is not a roughly uniform distribution of galaxy clusters with occasional dense concentrations. It is a web, a network of filaments and sheets surrounding vast, nearly empty regions, and the web's existence carries implications for the origin of all structure in the universe, from the smallest galaxy to the largest connected feature the sky contains. George Abell spent 2 years in the late 1950s examining the photographic plates of the Palomar Sky Survey, a comprehensive photographic atlas of the northern sky produced by the 48-inch Schmidt telescope at Palomar Observatory between 1950 and 1958. The survey covered roughly 70% of the sky on glass plates, each plate representing a 6-degree square region, and the complete set ran to nearly 1,000 plates. Abell went through them systematically, looking for concentrations of galaxies, regions where the projected density of galaxy images on the plate was high enough to indicate a physical cluster rather than a chance alignment. He identified 2,712 clusters in the northern sky, published in his 1958 catalog, applying a set of criteria that defined a cluster by the number of galaxies within a specified projected radius and brightness range. The Abell catalog became the primary reference for galaxy cluster studies for decades, and clusters identified by their Abell numbers still appear routinely in the cosmological literature. What Abell noticed and noted in his catalog paper was that the clusters were not uniformly distributed across the sky. Some regions contained many Abell clusters in close angular proximity. Others contained few. This non-uniform distribution suggested that clusters were themselves aggregated into larger structures, what Abell called second-order clusters, concentrations of clusters. The evidence was statistical and the interpretation uncertain, but the pattern was real enough that subsequent work pursued it seriously. Gérard de Vaucouleurs had been arguing for a similar conclusion from a different direction since the early 1950s. Working at observatories in Australia and later at the University of Texas, de Vaucouleurs mapped the distribution of galaxies in the nearby universe and found that the local group Andromeda and the surrounding galaxies were not distributed randomly but concentrated in a flattened region he called the local supercluster, a large-scale structure centered on the Virgo cluster, roughly 54 million light-years from the Milky Way, containing perhaps 1,300 or more galaxies in the cluster itself, and many more in the surrounding region. The local group sits near the supercluster's periphery, in a relatively low-density outlying region, drawn gravitationally toward the Virgo cluster at a rate that slightly retards the local group's expansion away from it, a perturbation called the Virgo-centric flow, detectable in the peculiar velocities of nearby galaxies. De Vaucouleurs' supercluster was not immediately accepted. The consensus through much of the 1960s held that the universe was, at the relevant scales, essentially homogeneous, that any apparent large-scale structure was a statistical artifact of incomplete sampling or the tendency of human pattern recognition to find clusters where none existed. The homogeneity assumption was not arbitrary. It was built into the theoretical framework of relativistic cosmology, which required the universe to be roughly uniform at large scales for the Friedmann equations to apply cleanly. Evidence for large-scale structure was, in this context, evidence against the standard model, and it was scrutinized accordingly. The scrutiny was resolved not by theoretical argument, but by redshift surveys, the systematic measurement of galaxy velocities using their spectral redshifts as a proxy for distance, allowing the construction of three-dimensional maps of galaxy positions, rather than the two-dimensional projected distributions visible in photographic surveys. A redshift combined with the Hubble relation gives a distance. A distance combined with an angular position gives a location in three-dimensional space. The first large redshift surveys, conducted through the 1970s and early 1980s, began to reveal that the three-dimensional distribution of galaxies was strikingly different from the two-dimensional distribution, and strikingly different from a uniform distribution in three dimensions as well. Margaret Geller and John Huchra led the Center for Astrophysics Redshift Survey through the 1980s from the Harvard-Smithsonian Center for Astrophysics in Cambridge. The survey was methodical and cumulative, measuring redshifts for galaxies in a series of thin slices of sky. Narrow declination bands scanned systematically across the sky, and building up the three-dimensional map slice by slice. The first complete slice, covering a 6-degree wide band across the northern sky and containing redshifts for roughly 1,100 galaxies, was published in 1986. The map it produced was not what a uniform or even a gently clustered distribution would have looked like. The galaxies were arranged in filaments and sheets surrounding large regions that were nearly empty of galaxies. the voids, and the overall pattern had the quality of a structure rather than a statistical fluctuation. The 1989 extension of the survey deepened the picture. Geller and Hucra, with their colleagues, had been accumulating redshifts in the direction of the Coma supercluster, a massive concentration of galaxies about 320 million light-years away, one of the richest known clusters, which Zwicky had studied decades earlier. As the data accumulated and the three-dimensional map of that region took shape, a feature emerged that extended across the full width of the survey slice. A sheet of galaxies roughly 500 million light-years long, 200 million light-years wide, and perhaps 15 million light-years thick, running across the survey like a wall. Geller and Hucra called it the Great Wall. It was the largest structure identified in the universe at the time of its publication, and its existence indicated that coherent structures, not merely statistical density enhancements, but genuinely connected features, existed at scales far larger than any theoretical model had predicted or required. The Great Wall forced a reckoning with the question of how such structures could form. In the standard picture of structure formation, matter in the early universe was distributed nearly uniformly, with tiny density fluctuations, the 1 part in 100,000 variations that the cosmic microwave background would later be shown to record, that grew under gravity over billions of years into the clusters and superclusters observed today. The timescale required to grow a coherent structure 500 million light-years long from those initial fluctuations was, in some theoretical frameworks, longer than the age of the universe. The Great Wall was not impossible, but it was uncomfortable, and subsequent surveys, larger, deeper, covering more sky, were partly motivated by the need to establish whether the Great Wall was a typical feature or an unusual one, and whether still larger structures awaited discovery. The Laniakea supercluster, identified and named by R. Brent Tully and colleagues in 2014, represented a different kind of structural mapping than the redshift surveys had produced. Rather than tracing the positions of galaxies, Tully's team mapped the peculiar velocities of galaxies, the component of each galaxy's motion that deviates from the smooth Hubble flow, reflecting the gravitational influence of nearby mass concentrations. In regions where matter is concentrated, galaxies on all sides are pulled toward the concentration, producing converging flows. In voids, galaxies are pushed outward, producing diverging flows. By mapping these velocity flows across a large volume of the nearby universe, Tully's team identified the watershed, the surface in three-dimensional space where the velocity flow transitions from converging to diverging, that defines the boundary of a coherent gravitational basin. The basin they mapped was vast, Laniakea. The name comes from the Hawaiian words for immeasurable heaven, stretches approximately 520 million light-years across, and contains roughly 100,000 galaxies, with a total mass estimated at around 1017 solar masses, or 100 quadrillion times the mass of the Sun. The Milky Way, the local group, the Virgo cluster, and the broader Virgo supercluster that de Vaucouleurs had mapped are all embedded within it, drawn toward a region of strong gravitational convergence near its center that had been identified years earlier as the Great Attractor, a mass concentration in the direction of the Centaurus and Norma constellations, partially obscured by the dust of the Milky Way's disk, that exerts a detectable gravitational pull on the local group and thousands of other galaxies throughout the region. Beyond Laniakea and abutting it lie other superclusters: the Perseus-Pisces supercluster, the Coma supercluster, the Shapley supercluster, the most massive known concentration of galaxies in the nearby universe, containing tens of thousands of galaxies in a region about 650 million light-years away and exerting its own gravitational influence on the surrounding volume. These superclusters are themselves connected by filaments of galaxies and separated by voids, and the network they form is the cosmic web, a structure that extends in some form across the entire observable universe. The voids that separate the filaments and sheets are not empty in the strict sense. They contain some galaxies distributed sparsely through their interiors, and they are threaded by thin filaments of gas and dark matter that the densest optical surveys begin to detect. But they are as close to empty as any large region of the universe gets. Volumes hundreds of millions of light-years across, containing perhaps 1/10 the average cosmic density of matter. The Bhuta's void, discovered in 1981 and discussed more fully in a later chapter, was among the first recognized, and its scale, roughly 250 to 330 million light-years across, was startling enough that it generated immediate debate about whether such emptiness was compatible with standard structure formation models. The voids have since been recognized as a fundamental structural element of the cosmic web rather than anomalies, their boundaries defined by the same processes of gravitational collapse that built the filaments and sheets. Computer simulations of cosmic structure formation, run with increasing sophistication since the 1980s, produce a cosmic web that closely matches the observed one, starting from initial density fluctuations consistent with those measured in the CMB, and evolving them forward under gravity, including the gravitational influence of dark matter, which dominates the mass budget and drives the collapse of structure. The simulations generate filaments, sheets, voids, and clusters in proportions and at scales consistent with what the redshift surveys have mapped. The match is not perfect, and the simulations require the inclusion of processes: star formation, feedback from supernovae and active galactic nuclei, the behavior of baryonic gas, that are modeled with approximations rather than derived from first principles. But the large-scale structure that emerges from these simulations was predicted before the largest surveys confirmed it, which is among the more striking validations of the theoretical framework. The homogeneity that de Vaucouleurs' critics had assumed, the universe as smooth at large scales, turns out to be real but conditional. Below approximately 300 million light-years, the universe is demonstrably inhomogeneous. Structure exists at every scale examined, from individual galaxies through clusters, superclusters, filaments, and walls, each level of organization connected to and dependent on the levels around it. Above that threshold, the distribution of matter begins to average out. Statistical measures of galaxy clustering, the two-point correlation function, the power spectrum of density fluctuations, show that at scales exceeding roughly 300 million light-years, the universe is consistent with the cosmological principle. Homogeneous and isotropic, looking the same in all directions and from all locations. The cosmic web is real, and it is bounded not by a physical edge, but by the scale at which its structures wash out into the background. That boundary, the scale at which structure gives way to statistical uniformity, is not merely an observational detail. It is the scale above which the universe's large-scale geometry can be described by the Friedmann equations, the solutions to Einstein's field equations that govern the universe's expansion. Below it, the equations break down as exact descriptions because the matter distribution is not uniform enough for the approximation to hold. The cosmic web is, in this sense, the limit of local complexity, the largest organized thing in the universe before the universe itself, homogeneous in aggregate, takes over. Chapter 7: The Observable Universe. In 1948, George Gamow and his graduate student Ralph Alpher submitted a paper to Physical Review titled "The Origin of Chemical Elements." The paper described a calculation. If the early universe had been extremely hot and dense, the nuclear reactions occurring in the first few minutes after the Big Bang would have produced hydrogen and helium in proportions close to what astronomers actually observed. Roughly 3 parts hydrogen to 1 part helium by mass, a ratio that stellar nucleosynthesis alone could not account for. The calculation worked. The predicted abundances matched the observed ones well enough to constitute genuine evidence for a hot early universe, and the paper became one of the founding documents of Big Bang cosmology. Gamow characteristically added Hans Bethe's name to the author list without asking him, for the sole reason that Alpher, Bethe, and Gamow aligned with the first 3 letters of the Greek alphabet. Bethe had not contributed to the paper. He accepted the credit graciously. The paper is still referred to in the literature as the Alpha-Beta-Gamma paper, which was exactly the effect Gamow had intended. Embedded within the calculation, in a section that received less immediate attention than the nucleosynthesis result, was a prediction about the present state of the universe. Alpher and his colleague Robert Herman worked out the implication fully in a separate paper later that year. If the early universe had been hot enough for the nuclear reactions the Alpha-Beta-Gamma paper described, it would have been filled with radiation, a thermal bath of photons in equilibrium with the hot plasma. As the universe expanded and cooled, that radiation would not disappear. It would persist, its temperature declining with the expansion, still filling all of space. By 1948, they calculated, it should have cooled to approximately 5 Kelvin, 5 degrees above absolute zero, and should be detectable as a faint glow of microwave radiation arriving equally from all directions. Nobody looked for it for 15 years. The observable universe is defined by this radiation's origin, and by the geometry that determines how far any signal can have traveled since the beginning. Working out that geometry requires holding 2 numbers in mind simultaneously, because they appear to contradict each other, and the contradiction is instructive. The universe is approximately 13.787 billion years old. One might therefore expect that the observable universe has a radius of 13.787 billion light-years, the distance light could travel in that time. The actual radius of the observable universe is approximately 46.5 billion light years. The difference between these two numbers is not an error. It is a consequence of the expansion of space during the time the light was traveling. When a photon leaves a distant galaxy and begins its journey toward us, the space it is traveling through is expanding. The photon moves through space at the speed of light, but the space itself is stretching, carrying the photon's origin point steadily farther away even as the photon travels toward us. By the time the photon arrives, the galaxy that emitted it has been carried much farther away than the photon's travel time alone would suggest. The comoving distance. The distance to that galaxy as measured in the universe's current coordinate system, accounting for all the expansion that has occurred since the photon was emitted, is what the 46.5 billion light-year figure represents. The galaxy whose light is just now reaching us from the edge of the observable universe was much closer when it emitted that light, perhaps only a few billion light-years away. But the expansion of space in the intervening 13.787 billion years has carried it to its current comoving distance of 46.5 billion light-years. The particle horizon, the boundary of the observable universe, is not a physical edge in any material sense. There is no wall there, no change in the character of space, no surface that a hypothetical traveler would cross and notice. It is a limit imposed by time and expansion. Beyond it, no signal has had time to reach us since the Big Bang, not because the universe does not extend beyond it, but because the light from those regions has not yet arrived. Everything beyond the particle horizon is, from our perspective, causally disconnected, not permanently in principle, since in a universe that expanded more slowly, light from those regions would eventually arrive. But currently, given the universe's age and the expansion history that has actually occurred, the Hubble radius is a related but distinct concept, and the distinction is worth holding. The Hubble radius, approximately 14 billion light-years, is the distance at which the recession velocity of a galaxy, due to the expansion of space, equals the speed of light. Beyond this distance, galaxies are currently receding faster than light. This does not violate relativity because the recession is not motion through space, but the expansion of space itself, and relativity's speed limit applies to motion through space rather than to the stretching of the coordinate system. Counterintuitively, light from galaxies beyond the Hubble radius can still reach us. A photon emitted from beyond the Hubble radius is initially being carried away faster than it can travel toward us. But if it is emitted in our direction, it moves into regions of progressively lower recession velocity as it travels inward. In a universe where the Hubble radius is growing, as it was during the matter-dominated era, the photon eventually finds itself within the Hubble radius and can complete its journey. The particle horizon at 46.5 billion light-years is thus substantially larger than the Hubble radius at 14 billion light-years, because light emitted from beyond the Hubble radius in the early universe was able, over billions of years, to work its way inward to reach us. The observable universe contains, within its 46.5 billion light-year radius, an estimated 2 trillion galaxies. This figure, published in 2016 by Christopher Consolis and colleagues at the University of Nottingham, was itself a revision, upward by roughly a factor of 10, of the previous standard estimate of around 200 billion galaxies. The revision came not from a new survey detecting previously unknown galaxies, but from a mathematical argument about the galaxies that existing surveys could not detect. Consolise's team analyzed the evolution of galaxy number density across cosmic time, using data from deep surveys reaching back to when the universe was less than 1 billion years old. They found that the number of galaxies per unit volume was much higher in the early universe than it is today. Most small galaxies have merged into larger ones over time, so that counting galaxies in the present-day universe undercounts the total number of independent structures that have existed. Correcting for this merger history and for the fraction of the universe too faint and distant for any current instrument to detect, they arrived at the 2 trillion figure. 2 trillion galaxies, each containing on average perhaps 100 billion stars. The total number of stars in the observable universe is therefore on the order of 1024 (-c), a number with no useful comparison at human scales, a number that resists the kind of grounding that makes measurements feel inhabited. What can be said is that the observable universe is not sparsely populated. Even the apparently empty regions of sky between visible objects are filled, at sufficient depth, with galaxies, a fact demonstrated most directly by the deep field observations that belong to a later chapter, and anticipated by the 2 trillion figures implication that a random line of sight through the observable universe passes through or near hundreds of galaxies at various distances. The homogeneity of the universe at the largest scales, the fact that the cosmic microwave background arrives at almost exactly the same temperature from every direction, the fact that the distribution of galaxies is statistically uniform above 300 million light-years, presents a puzzle when the particle horizon is taken seriously. 2 regions of sky on opposite sides of the observable universe are separated by approximately 93 billion light-years. They have never been in causal contact, no signal traveling at the speed of light since the Big Bang could have crossed from one to the other, because the observable universe is larger than light could have traversed in its lifetime. Yet they are at the same temperature to 1 part in 100,000. In a universe where temperature equilibrates through contact, where regions reach the same temperature because they have exchanged photons and reached thermal equilibrium, the uniformity of the CMB is inexplicable unless the regions we observe were once in contact. This is the horizon problem, and it is one of the 2 observational puzzles that the theory of cosmic inflation was constructed to resolve. Its resolution belongs to a later chapter. The age of the universe, 13.787 billion years, is itself a measured quantity rather than a derived one, determined primarily from the CMB. The pattern of temperature fluctuations in the microwave background encodes the geometry of the universe, the proportions of matter, and dark energy, and the rate of expansion at the time the CMB was produced, with sufficient precision that the age can be extracted from the data with an uncertainty of less than 1%. Independent measurements, the ages of the oldest stars in globular clusters, the decay of long-lived radioactive isotopes in ancient stellar material, the Hubble constant combined with the expansion history derived from supernova data, All converge on values consistent with this age, though the consistency is not exact, and the Hubble tension discussed in the previous chapter reflects a genuine discrepancy between different ways of inferring the universe's age and expansion history. 13.787 billion years is a long time in any frame of reference a human mind can inhabit, and it is simultaneously a short time in the frame of reference the observable universe itself provides. The universe will, on current understanding, continue to exist and evolve for timescales that dwarf its current age by factors that cannot be meaningfully compared. The stars currently forming in the Milky Way and in galaxies throughout the observable universe will burn for billions of years. The lowest mass red dwarf stars will continue burning for trillions of years, long after the Sun has exhausted its fuel and the Milky Way and Andromeda have merged and settled into an elliptical remnant. The observable universe at 13.787 billion years old is, in the timeline of stellar evolution, still early. The era of ordinary stars and galaxies is not finished, but is perhaps a third of the way through its natural span, after which the lights will begin going out one by one across a vastly larger and emptier observable volume. What the observable universe contains is, in this sense, a snapshot, not of a static condition, but of a particular moment in a long evolution. The 2 trillion galaxies that Consolis's census implies are not permanent features of the observable volume. Accelerating expansion will carry them progressively farther away. Eventually, in tens of billions of years, the recession of the most distant galaxies will carry them beyond the cosmic event horizon, the boundary beyond which no light emitted now will ever reach us, and they will fade permanently from the observable universe, leaving only the local group and its immediate neighbors within reach of any future observation. The observable universe is currently at its most populated moment. It will thin steadily from here. The 46.5 billion light-year radius is a boundary of information, not of existence. Nothing about the physics of space, matter, or energy changes at that distance. The universe, whatever its true extent, a question that belongs to a later chapter, does not end there, or thin, or transition into something different. The particle horizon is a feature of our position in time and space, the result of the specific age of the universe and the specific expansion history it has undergone. An observer in a different galaxy at the same cosmic time would have a different observable universe of the same size, centered on their location, overlapping with ours in the regions between us, but extending in their direction to regions entirely outside our reach. Every point in the universe is the center of its own observable sphere. The observable universe is not a place, it is a perspective. Chapter 8: The Cosmic Microwave Background. The horn antenna at Holmdel, New Jersey was built in 1959 to communicate with Echo 1, a large reflective balloon satellite that Bell Telephone Laboratories had helped develop for experimental passive communications relay. The antenna was a large metal horn, open at one end to collect radio waves reflected from the balloon's surface, precisely engineered to minimize stray signals from the ground and from the antenna's own structure. When the Echo program wound down and the antenna was no longer needed for satellite work. Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs, repurposed it in 1963 for radio astronomy. It was, in several respects, an unusually clean instrument. Its design had required extreme care in eliminating unwanted noise, which made it well suited to the kind of careful, absolute measurements that radio astronomy occasionally demanded. Testing the antenna's performance in 1964, Penzias and Wilson found a problem. There was noise in the system that could not be accounted for, a persistent hiss at a level corresponding to a temperature of approximately 3.5 Kelvin, coming equally from every direction they pointed the antenna. Noise in radio systems is measured in temperature units because thermal radiation produces a characteristic noise level proportional to temperature, and expressing noise as an equivalent temperature allows different sources to be compared and subtracted. The 3.5 Kelvin excess was not enormous, but it was real, it was stable, and it was present regardless of where in the sky the antenna pointed. Regardless of the time of day, regardless of the season. Sources of noise that varied with the antenna's direction or with time could be attributed to specific objects in the sky or to the rotation of the Earth relative to those objects. A noise that was constant across all directions was harder to explain. Penzias and Wilson went through the antenna systematically. They checked the receiver electronics, recalibrated the system temperature measurements, examined the waveguide connections between the horn and the receiver for sources of resistive loss that might contribute thermal noise. They found a pair of pigeons nesting in the horn's throat, common pigeons, Columba livia, apparently finding the large metal structure a congenial roosting location, and removed them, cleaning the interior of what Penzias later described in a scientific paper with careful understatement as a white dielectric material. The pigeons returned. The birds were relocated more permanently. The white dielectric material was cleaned again. The 3.5 Kelvin signal remained unchanged. They considered whether the noise might be coming from New York City, visible on the horizon from Holmdel. They considered whether it might be a residual effect of above-ground nuclear tests conducted a few years earlier, which had deposited radioactive material in the upper atmosphere. They considered instrumental effects they might have missed. None of these explanations held up against the signal's isotropy, its identical intensity from every direction, including directions well away from the city and well away from any atmospheric contamination. An isotropic signal of thermal character, arriving from the whole sky simultaneously, had no obvious local explanation. In early 1965, Penzias heard, through a circuitous path involving a preprint and a mutual contact, that a group at Princeton was working on a theoretical prediction that might be relevant. Robert Dicke, a physicist at Princeton with broad interests spanning experimental relativity, cosmology, and instrumentation, had arrived independently at the conclusion that a hot early universe should have left a relic radiation field. The same conclusion Alpher and Hermann had reached in 1948, but which had not registered widely in the astronomical community. Dick had assembled a small group to build an instrument specifically to search for this radiation. Jim Peebles was working out the theoretical predictions, and David Wilkinson and Peter Roll were constructing a small Dick radiometer on the roof of the Palmer Physical Laboratory. They were, in the language of experimental physics, scooped, not by a competing group pursuing the same goal, but by two radio astronomers who had found the signal while looking for something else entirely, or rather, while looking for nothing at all, trying to understand why their carefully engineered instrument was noisier than it should have been. Penzias called Dickie. Dick took the call at his desk, surrounded by the Princeton group. He listened to the description of the persistent isotropic noise at 3.5 Kelvin, and when Penzias finished, Dickie turned to his colleagues and said, according to accounts from those present, that they had been beaten. The four of them had been building an instrument to find what Penzias and Wilson had already found by accident. The two groups agreed to publish simultaneously, Penzias and Wilson reporting the observation, Dickie's group providing the theoretical interpretation. The papers appeared side by side in the Astrophysical Journal in 1965. Penzias and Wilson received the Nobel Prize in Physics in 1978. Dick, Peebles, Wilkinson, and Roll did not, an omission that has been noted as one of the more consequential oversights in the Nobel Committee's history. What Penzias and Wilson had detected was light from the earliest moment the universe became transparent. For the first 380,000 years after the Big Bang, the universe was hot enough that hydrogen could not exist as neutral atoms. Any electron that combined with a proton was immediately knocked free again by the energetic photons flooding the plasma. In this state, the universe was opaque. Photons scattered constantly off free electrons, traveling only tiny distances before being deflected, trapped in the hot plasma the way light is trapped inside the sun. At approximately 380,000 years, as the universe expanded and cooled below about 3,000 Kelvin, electrons and protons combined into neutral hydrogen atoms at a rate faster than the photons could ionize them. The universe became transparent almost suddenly, on cosmological timescales, and the photons that had been trapped in the plasma streamed freely outward in all directions. Those photons have been traveling ever since through an expanding universe, their wavelengths stretched by the expansion from the infrared into the microwave range, their temperature declining from 3,000 Kelvin to the 2.725 Kelvin measured today. They are the oldest light in the universe, and they arrive at every point in space from every direction simultaneously, because every point in the universe was inside that primordial plasma when it became transparent. The temperature Penzias and Wilson measured, 3.5 Kelvin, revised to the modern value of 2.725 Kelvin as calibration improved, was consistent with Alpher and Hermann's 1948 prediction of roughly 5 Kelvin, close enough given the uncertainties in their calculation that the match was immediately persuasive. The CMB was not merely a noise problem. It was the universe's earliest available record, a thermal remnant from an epoch preceding any galaxy, any star, any structure larger than quantum fluctuations in the hot plasma. The COBE satellite, the Cosmic Background Explorer, was launched in November 1989, carrying instruments designed to measure the CMB's spectrum and its spatial variation across the sky with a precision that ground-based and balloon-borne instruments could not achieve. John Mather led the team responsible for the spectral measurement instrument, the Ferris radiometer, which confirmed within the first 9 minutes of data that the CMB was an almost perfect blackbody spectrum, a thermal radiation distribution matching the theoretical shape expected from a source in thermal equilibrium, with a temperature of 2.725 Kelvin, to a precision that made it the most perfect blackbody ever measured in nature. The result was presented at an American Astronomical Society meeting in January 1990 to a standing ovation, a reception unusual enough in the context of a scientific conference that it was remarked upon in subsequent accounts of the event. The second COBE instrument, the DMR, was designed to look not at the CMB's average temperature, but at its variations, the tiny differences in temperature from one part of the sky to another that would reflect density variations in the early universe. Theory predicted such variations must exist. The large-scale structure observed today, the galaxies, clusters, and filaments of the cosmic web, had to have grown from something, and the something was density fluctuations in the early plasma. Without initial variations in density, gravity would have had nothing to amplify, and the universe would have remained uniform forever. The fluctuations had to be present at the time of last scattering, imprinted on the CMB as temperature variations. The question was whether they were large enough for COBE's instruments to detect. George Smoot led the DMR team. After 2 years of data collection and careful analysis, accounting for the CMB's dipole anisotropy, the slightly higher temperature in the direction the Earth is moving toward due to the Doppler effect of the solar system's motion through the CMB rest frame, and for emission from the Milky Way's own disk, Smoot's team announced in April 1992 that they had detected temperature fluctuations in the CMB at the level of roughly 1 part in 100,000. Stephen Hawking, asked for comment, called it the greatest discovery of the century, possibly of all time, a characterization whose extravagance reflected the genuine weight of the finding. The fluctuations were there. They had the right statistical properties, the right pattern of variation at different angular scales, to be the seeds of the structure observed in the universe today. Mather and Smoot shared the 2006 Nobel Prize in Physics for the COBE results. COBE's angular resolution was limited to about 7 degrees. It could detect the fluctuations, but could not map them in detail. The WAMAP satellite, launched in 2001 and operating until 2010, mapped the CMB temperature fluctuations at an angular resolution of about 0.3 degrees, revealing the detailed structure of the temperature pattern across the full sky. The Planck satellite, launched in 2009 by the European Space Agency and operating until 2013, improved this further to a resolution of about 5 arc-minutes, producing the most detailed map of the CMB currently available, a full sky image in which temperature variations of millionths of a Kelvin are resolved across angular scales from the full sky down to features less than 1/10 of a degree across. The pattern in the Planck map is not random noise. It has a specific statistical structure, a characteristic angular scale at which the fluctuations are most pronounced, produced by acoustic oscillations in the early plasma. In the first 380,000 years, the universe was a hot plasma in which pressure and gravity competed. Gravity pulled matter together, pressure pushed it apart, and the competition produced oscillations, sound waves, in a broad sense, propagating through the plasma. The characteristic angular scale visible in the CMB corresponds to the distance that sound could travel through the plasma in 380,000 years. The sound horizon frozen into the temperature pattern at the moment of last scattering. This scale, measured precisely in the CMB, provides an absolute standard ruler, a known physical length imprinted on the sky at a known distance from which the geometry of the universe, whether it is spatially flat, positively curved, or negatively curved, can be determined. The Planck data indicate that the universe is spatially flat to within measurement precision, with a total energy density extremely close to the critical density that separates an open from a closed geometry. The acoustic oscillations are not merely present in the CMB, they are present in the distribution of galaxies as well, as a slight excess of galaxy pairs separated by a specific distance, approximately 490 million light-years in today's coordinates, corresponding to the same sound horizon scale, now expanded by the universe's expansion since last scattering. This feature, called baryon acoustic oscillations, was detected in galaxy surveys in 2005 and has since become an independent cosmological ruler, confirming the acoustic scale measured in the CMB and providing another means of tracing the universe's expansion history. The same oscillation that Penzias and Wilson's antenna noise contained, buried in a signal they could not explain, echoes through the large-scale distribution of galaxies across the observable universe. The photon that arrives at a radio antenna in New Jersey, or at the detector array of a satellite orbiting the second Lagrange point, departed from its last scattering surface approximately 13.4 billion years ago, when the universe was 380,000 years old. At that moment, the photon was an infrared photon emitted from hydrogen plasma at roughly 3000 Kelvin. It traveled outward through space that was expanding, its wavelength stretching continuously as the space it was crossing grew, spending billions of years crossing distances no structure had yet organized, passing through regions where galaxies had not yet formed and regions where they had, arriving finally at a detector that was not built until 13.4 billion years after the photon began its journey. The photon carries no memory of any of this. It carries only the temperature variation, the slight excess or deficit of energy relative to the mean that was imprinted on it at the last scattering surface. A record of the density of the plasma at that point in space and time, which is now part of the most detailed map of the early universe that human instruments have yet produced. Chapter 9: Dark Matter and the Hidden Architecture. The rotation curves were wrong. Not wrong in the sense that the measurements were poorly made or the instruments unreliable. The measurements were careful and the instruments were well calibrated, but wrong in the sense that the numbers produced by observation did not match the numbers predicted by the distribution of visible matter. Stars in the outer regions of spiral galaxies were moving too fast. They were moving at speeds that, given the amount of mass that could be seen, the stars, the gas, the dust detectable by optical and radio instruments, should not have been gravitationally sustainable. At those velocities, the outer regions of galaxies should have been flying apart, the stars escaping into intergalactic space rather than completing their orbits. They were not flying apart. They were orbiting steadily at velocities that implied a quantity of mass several times larger than anything the telescopes could account for. The discrepancy had been noticed before Vera Rubin and Kent Ford made it the subject of systematic investigation. Fritz Zwicky, a Swiss astronomer working at the California Institute of Technology, had measured the velocities of individual galaxies within the Coma cluster in 1933, using the Doppler shifts in their spectra to determine how fast each galaxy was moving relative to the cluster's center of mass. The velocity dispersion he found, the spread of velocities around the mean, was approximately 1,000 kilometers per second, a figure that implied through the virial theorem relating kinetic energy to gravitational potential energy in a bound system, a total cluster mass roughly 400 times larger than the mass visible in the cluster's galaxies. Zwicky concluded that most of the cluster's mass was in a form he called dunkel materia, dark matter. The observation was real, the reasoning was sound, and the conclusion was largely ignored for 4 decades. The measurement was difficult. The Coma cluster's distance introduced calibration uncertainties, and the idea of large quantities of invisible mass distributed through galaxy clusters had no natural place in the theoretical frameworks then current. Zwicky noted it, published it, and the field moved on. Sinclair Smith independently reached a similar conclusion for the Virgo cluster in 1936, finding the same order of magnitude discrepancy between the dynamical mass implied by galaxy velocities and the luminous mass visible in stars. Jan Oort found evidence for unseen mass in the disk of the Milky Way in 1932, measuring the vertical motions of stars above and below the galactic plane and inferring from them a local mass density somewhat higher than the visible stars could account for. These observations accumulated at the periphery of the field's attention without coalescing into a recognized problem, partly because each measurement carried individual uncertainties, and partly because there was no theoretical framework to give the accumulating discrepancies a coherent meaning. Vera Rubin arrived at the Carnegie Institution of Washington in 1965 after a career navigating institutional barriers that had kept women from the major observatories for most of her early professional life. She had been denied admission to Princeton's graduate astronomy program in the early 1950s because the program did not accept women. She completed her doctorate at Georgetown instead, working on the large-scale motions of galaxies in a thesis that drew little immediate recognition but anticipated later developments in the study of large-scale structure. At Carnegie, working with Kent Ford, who had developed an exceptionally sensitive spectrograph using image intensifier technology that allowed spectral measurements of faint objects in exposure times far shorter than previously required, Rubin began a systematic study of galaxy rotation curves. The method was straightforward in principle. A spectrograph slit was placed along the major axis of a spiral galaxy, the axis running through the center parallel to the disk's longest dimension, and a spectrum was obtained for each position along the slit simultaneously. The absorption or emission lines in the spectrum at each position were Doppler shifted by the rotation of the galaxy. On the side of the galaxy rotating toward the observer, the lines shifted to shorter wavelengths. On the side rotating away, they shifted to longer wavelengths. The magnitude of the shift at each position along the slit gave the rotation velocity at that galactic radius. Plotting rotation velocity against distance from the center produced the rotation curve, the relationship between orbital speed and orbital radius that encoded the distribution of mass within the galaxy. The expectation derived from the observed distribution of light in spiral galaxies and the reasonable assumption that mass traced light was a specific shape, rising steeply in the inner regions where stars were densely packed, reaching a peak somewhere near the edge of the bright disk, and then declining in the outer regions as the enclosed mass became approximately constant and orbital mechanics required more distant stars to move more slowly, in the way that outer planets move more slowly than inner ones. This Keplerian decline, named for Johannes Kepler, whose laws described planetary orbital velocities, was what every theoretical model predicted for the outer regions of spiral galaxies. Rubin and Ford did not find it. Their first systematic study, published in 1970, examined the Andromeda galaxy in detail, measuring rotation velocities at distances far into the galaxy's outer disk where the Keplerian decline should have been clearly visible. The rotation curve was flat. The velocity at large radii was essentially the same as the velocity in the inner disk, showing no decline out to the farthest radii where the measurements could be made reliably. Subsequent work extended this finding to dozens of other spiral galaxies. The flatness was not specific to Andromeda. It was a general property of spiral galaxies, present in systems of different sizes, different luminosities, different morphological types. Wherever the rotation curve could be measured at large radii, and Ford's spectrograph allowed this to be done with a reliability and consistency that previous instruments had not permitted. It was flat. A flat rotation curve implies a specific relationship between mass and radius. For orbital velocity to remain constant as radius increases, the mass enclosed within any given radius must increase linearly with that radius. Double the radius, double the enclosed mass. This means that mass is not concentrated in the bright disk of the galaxy, but continues to increase at large radii, in regions where little or no light is detected. The mass distribution that produces a flat rotation curve is a roughly spherical halo of matter extending far beyond the visible disk, with a density that falls off as the inverse square of the distance from the center, present at large radii in quantities far exceeding the visible stellar population, yet emitting no detectable radiation at any wavelength the instruments could access. The invisible mass was not merely absent from optical surveys. It was absent from radio surveys mapping the 21 centimeter hydrogen emission. It was absent from infrared surveys sensitive to cool stars too faint to detect optically. It was absent from X-ray surveys sensitive to hot gas. Whatever it was, it did not emit, absorb, or scatter electromagnetic radiation in any form that had been detected across the entire spectrum from radio to gamma ray. It interacted gravitationally. Its presence was detectable only through its effect on the motions of the visible matter around it. This combination of properties, gravitational interaction, electromagnetic inertness, defined what the field came to call dark matter, a term Zwicky had used 4 decades earlier for a different observational discrepancy that turned out to have the same explanation. The reception of Rubin and Ford's results was measured rather than immediate. The implications were large enough that alternative explanations were sought seriously. Perhaps the rotation curves reflected the dynamics of a non-Newtonian gravitational theory at low accelerations. Perhaps the measurements were systematically biased in ways not yet identified. Perhaps the mass discrepancy reflected ordinary matter in some dark form: brown dwarf stars, black holes, cold gas clouds that had escaped detection. Each alternative was examined, and each failed in some respect to account for the full pattern of observations. Modified Newtonian dynamics, MOND, proposed by Mordechai Milgram in 1983, could reproduce the rotation curves of individual galaxies with reasonable accuracy, but struggled to account for the dynamics of galaxy clusters and the large-scale structure of the universe. Dark baryonic matter in the form of compact objects was constrained by gravitational microlensing surveys, which found fewer compact objects than the dark matter density required. The alternatives narrowed, and the non-baryonic dark matter hypothesis, matter made of particles not in the standard model of particle physics, interacting gravitationally but not electromagnetically, came to dominate the field's working assumptions. The bullet cluster provided the most direct observational case for dark matter as a distinct component separate from ordinary baryonic matter. The bullet cluster, officially designated 1E0657558, is a system of two galaxy clusters that have passed through each other, the smaller cluster having moved through the larger one and emerged on the other side in a configuration observed approximately 100 to 150 million years after the collision. When two clusters collide, the galaxies within them, which are mostly empty space, pass through each other largely without interaction, continuing their trajectories relatively undisturbed. The hot gas that fills each cluster, comprising the majority of the cluster's baryonic mass, experiences ram pressure as it collides with the gas of the other cluster, slowing and compressing into a shock front visible in X-ray emission, the bullet shape that gives the system its name. The Chandra X-ray Observatory mapped the hot gas distribution in 2006, locating the bulk of the baryonic mass in the post-collision region between the two clusters, where the gas had been slowed and concentrated by the collision. Gravitational lensing, the bending of background galaxy images by the cluster's mass, independently mapped the total mass distribution. The two maps did not coincide. The mass distribution traced by gravitational lensing was centered not on the hot gas, but on the galaxies, on the two cluster cores that had passed through each other and continued moving apart, carrying with them a mass component that had not been slowed by the collision the way the gas had been. The lensing mass was where the galaxies were, not where the gas was, and the galaxies alone were not massive enough to account for the lensing signal. The inferred mass in the galaxy cores, in the form of a component that had passed through the collision without interacting with the opposing cluster's gas, was several times larger than the visible stellar mass and had the properties expected of dark matter. It interacted gravitationally, it did not interact electromagnetically, and it had passed through the collision as if the opposing cluster's ordinary matter were not there. Dark matter, on current cosmological measurements, constitutes approximately 27% of the universe's total energy density. Ordinary baryonic matter, the protons, neutrons, and electrons that make up stars, gas, planets, and everything directly observable, constitutes approximately 5%. Dark energy, the component driving the accelerating expansion, accounts for the remaining 68%. The universe is, in this accounting, approximately 95% composed of things whose fundamental nature remains undetermined. Dark matter whose particle identity has not been established, and dark energy whose physical mechanism is unknown. Laboratory searches for dark matter particles. Detectors bury deep underground to shield them from cosmic rays, designed to detect the rare collision of a dark matter particle with an atomic nucleus, have so far not produced a confirmed detection, constraining but not eliminating the most theoretically favored candidate particles. Searches at particle colliders have similarly found no confirmed dark matter candidates. The evidence for dark matter's existence and its overall density is robust. The evidence for what dark matter actually is remains absent. The galaxy at the center of what dark matter explains is not merely the rotation curve of a single system, but the entire architecture of large-scale structure. The cosmic web of filaments and voids that redshift surveys revealed, described in an earlier chapter, matches the predictions of simulations that include dark matter far better than simulations without it. Dark matter's gravitational influence provided the scaffolding along which ordinary matter collected, the density enhancements in the early universe that gravity amplified into the filaments and sheets of the cosmic web. Without dark matter, the density fluctuations in ordinary matter alone would not have had time to grow into the structures observed today. The gravitational amplification of baryonic fluctuations was too slow, suppressed by the coupling of baryons to photons in the early plasma. Dark matter, which decoupled from radiation much earlier, began forming gravitational potential wells that baryonic matter fell into after decoupling, accelerating the formation of structure. The cosmic web is, in this sense, dark matter's most visible consequence. The pattern left by an invisible scaffold whose presence can only be read in the arrangement of the luminous matter it has gathered around itself. Chapter 10: The Large-Scale Structure. At scales below roughly 300 million light-years, the universe is a complicated place. Galaxies cluster, clusters aggregate into superclusters, superclusters connect through filaments, filaments bound voids, and the voids themselves vary in size and depth in ways that reflect the specific history of the region they occupy. Structure exists at every scale examined within this range, each level of organization embedded in and shaped by the levels above and below it, the whole arrangement specific enough that any two comparable volumes of the universe at these scales would look meaningfully different from each other. Above 300 million light-years, something changes. The specificity fades. The distribution of matter begins to average out, the variations in density from one region to another diminishing toward a statistical uniformity that persists at every larger scale subsequently examined. The universe above this threshold is not featureless. Structures of a kind still exist there, connected over billions of light years. But it is no longer organized in the way that the cosmic web is organized below it. It is tending toward homogeneity, and homogeneity, once reached, holds. This transition from structured to statistically uniform is not a sharp boundary, but a gradual smoothing, and establishing where it occurs and what it implies required surveys larger than anything the technology of the mid-20th century could support. The first evidence that large-scale structure existed at all came from the CFA surveys described in the previous chapter. The evidence that the structure had a limit, that the universe eventually became homogeneous, came from surveys larger by orders of magnitude, covering more galaxies and greater volumes than Geller and Hucra's pioneering slices, using spectrographs capable of measuring hundreds or thousands of galaxy redshifts simultaneously rather than one at a time. Jean Ionesco, an Estonian astronomer working through much of his career in the Soviet system at the Tartu Observatory, was among the first to map the void and supercluster structure of the nearby universe with enough completeness to argue that the pattern was real rather than artifactual. Working through the 1970s with colleagues including N. Saar and Mikhail Jovier, Ionescu compiled the available redshift data for galaxies in selected regions of sky and found a clear alternation between concentrations and near-empty regions, a cellular structure in which superclusters formed the walls of cells surrounding interior voids. His 1978 paper with Jovier and Saar, presented at an IAU symposium in Tallinn, described this cellular structure and identified specific voids and supercluster filaments with enough precision to constitute genuine discovery. The work was done with the limited redshift data available in the Soviet astronomical literature at the time, supplemented by what could be obtained from Western sources, and it reached conclusions that larger subsequent surveys would confirm and extend. The void that forced the question of large-scale structure into sharper focus was found not in a systematic survey, but in a targeted investigation of an apparent gap in the galaxy distribution. Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman were measuring galaxy redshifts in selected directions of sky in 1981 as part of a program to study the clustering properties of galaxies in fields chosen for their apparent sparseness. In the direction of the constellation Bootes, they found a region of sky covering several degrees on a side and extending across a substantial redshift range that contained, within a volume they calculated at roughly 250 to 300 million light-years across, almost no galaxies at all. The survey found 5 galaxies where statistical estimates based on the average galaxy density suggested there should have been around 2,000. Kirshner's group called it the Bootes void. The name was direct and the measurement was clear, but the implication took time to absorb. A region 250 to 330 million light-years across, nearly empty of galaxies, was not something that existing models of structure formation had predicted or accommodated comfortably. The standard picture of structure formation, density fluctuations growing under gravity from a smooth initial distribution, produced voids, but voids of this scale required either very large initial fluctuations or very long growth times, and the available estimates of both were insufficient. The Buddha's void was not impossible, but it was at the edge of what the theory could explain without modification, and its discovery prompted immediate theoretical attention to the question of how large structures, overdense and underdense alike, could grow to their observed sizes within the universe's age. Subsequent surveys established that the Buddha's void, while large, was not uniquely so. The universe contains many voids of comparable or greater size, distributed through the cosmic web as its dominant volumetric component. The voids occupy the majority of the universe's volume, while the galaxies, clusters, and filaments occupy a minority of the volume but contain most of the mass. The Buddha's void was the first clearly identified example of a class of structure that turned out to be ordinary, which is itself a fact worth registering. The universe is, by volume, mostly empty, and the emptiness is organized into coherent regions whose boundaries are defined by the surrounding filaments and sheets of the cosmic web. The Sloan Digital Sky Survey began operations in 2000 from Apache Point Observatory in New Mexico, using a dedicated 2.5-meter telescope equipped with a wide-field camera capable of imaging 1.5 square degrees of sky simultaneously, and a pair of spectrographs capable of measuring the redshifts of 640 galaxies in a single exposure. The survey's design was systematic in a way that previous redshift surveys had not been. A contiguous area of sky in the northern galactic cap, observed stripe by stripe until the full planned footprint was covered, with well-defined selection criteria applied uniformly across the survey volume. By the time the survey's main galaxy redshift program concluded, it had measured spectra and redshifts for approximately 930,000 galaxies, with additional programs extending coverage to quasars, rare objects, and the southern sky. Later data releases, incorporating additional programs and extended observing, brought the total to several million objects. The three-dimensional map of galaxies produced by SDSS was qualitatively similar to what the CFA surveys had shown in their smaller volumes: filaments, walls, and voids, but extended to distances and volumes that made statistical analysis meaningful at scales where the CFA data had been too sparse to draw firm conclusions. The map revealed that the cellular structure Einasto had described in 1978, the filaments and voids of the cosmic web, persisted to the limits of the survey's depth, roughly 2 billion light-years in the most densely sampled regions, without any sign of breaking down into featurelessness until the analysis reached scales approaching and exceeding 300 million light-years. Within the SDS volume, J. Richard Gott, Mario Urich, and colleagues identified in 2005 what they called the Sloan Great Wall, a filamentary concentration of galaxy clusters roughly 1.37 billion light-years long, 80 million light-years wide, and 15 million light-years thick, located approximately 1 billion light-years from Earth in the direction of the constellations Leo and Corvus. The Sloan Great Wall was at its discovery the largest known structure in the universe, surpassing Geller and Hukra's Great Wall by a factor of nearly 3 in length. It held the record briefly. Subsequent analyses of SDSS and other survey data have identified candidate structures of comparable or greater extent. The Hercules Corona Borealis Great Wall, reported in 2013 from a study of gamma-ray burst positions, extends across several billion light-years if the association of gamma-ray bursts with large-scale structure is correctly interpreted. Though this identification remains contested, and the object's status as a coherent structure rather than a statistical fluctuation is not universally accepted. The contested status of the largest candidate structures illustrates a general point about the upper limit of cosmic organization. As structures become larger, the evidence for their coherence, for the claim that a given collection of galaxies or clusters constitutes a single connected entity rather than a chance alignment along the line of sight or a statistical fluctuation in a uniform distribution, becomes harder to establish. A cluster of galaxies at a common redshift with common internal dynamics and a common X-ray emitting gas atmosphere is clearly a coherent physical object. A filament of clusters identified in a redshift survey is somewhat less obviously coherent, but still physically motivated by the dynamics of gravitational collapse along the axes of dark matter filaments. A wall of clusters a billion light-years long, identified by statistical overdensity in a redshift catalog, is harder to characterize as a single physical structure, and a wall of several billion light-years identified through the positions of rare transient events is harder still. The concept of a coherent structure becomes ambiguous at scales where the universe's expansion is pulling the constituent parts apart faster than gravity can hold them together. Baryon acoustic oscillations. The imprint of the early universe's acoustic oscillations on the galaxy distribution, introduced in the previous chapter in the context of the CMB, provided the SDSS data with a new kind of structural analysis that operated differently from simple identification of overdensities. Rather than mapping the positions of structures directly, baryon acoustic oscillation analysis looks for a statistical excess of galaxy pairs separated by a specific distance, approximately 490 million light-years in today's comoving coordinates. The scale of the sound horizon at last scattering expanded to the present by the universe's subsequent growth. Daniel Eisenstein and colleagues detected this excess in the SDS luminous red galaxy sample in 2005, confirming that the acoustic scale visible in the CMB was also present in the distribution of galaxies, as expected if both reflected the same primordial oscillations in the early plasma. The acoustic scale provides a standard ruler in the galaxy distribution, a known physical length calibrated by the CMB measurements, whose apparent size at different redshifts traces the universe's expansion history. Surveys measuring the baryon acoustic oscillation signal at multiple redshifts effectively measure how far apart galaxies with a known physical separation appear to be at different cosmic epochs, extracting from this the rate at which the universe expanded between those epochs. This technique has become one of the primary tools for measuring the expansion history and constraining the properties of dark energy, independent of the supernova standard candle method, and it operates at the scale of the large-scale structure itself, using the universe's own largest coherent statistical feature as the measuring instrument. The cosmological principle, the assumption that the universe is homogeneous and isotropic at sufficiently large scales, that it looks the same in all directions and from all positions, sits beneath the entire framework of relativistic cosmology as both an observational claim and a working assumption. As an observational claim, it is supported by the isotropy of the CMB to 1 part in 100,000, by the convergence of galaxy counts toward uniformity at scales above 300 million light-years, and by the consistency of cosmological parameters derived from widely separated regions of the sky. As a working assumption, it is required for the Friedmann equations, the solutions to Einstein's field equations that describe a uniform, expanding universe, to apply as more than approximations. A universe that remained inhomogeneous at arbitrarily large scales would require a different mathematical framework for its description, and the concordance between the Friedmann model predictions and the full range of cosmological observations would require explanation. The transition to homogeneity at 300 million light-years is the observational basis for the cosmological principle's application. Below that scale, the principle fails as a description. The universe is manifestly inhomogeneous, organized into structure that is specific and varied. Above it, the principle holds well enough that the Friedmann equations describe the universe's large-scale behavior with the precision that observations currently require. The large-scale structure, the filaments, walls, and voids of the cosmic web, the superclusters and their connections, the great walls that span hundreds of millions or billions of light-years, is everything that exists between the scale of individual galaxies and the scale at which the universe becomes, for practical cosmological purposes, smooth. It is bounded below by the processes that form galaxies, and above by the processes that make the universe isotropic. And within those bounds, it is the most complex organized thing that the universe contains. Chapter 11. Beyond the Horizon. The measurements run out before the universe does. This is not a temporary limitation waiting to be resolved by a better instrument or a more sensitive detector. It is a structural feature of the observable universe's relationship to whatever lies beyond it, a consequence of the specific age of the universe and the specific history of its expansion. The particle horizon is not a technological barrier, it is a causal one. No instrument, however refined, can receive a signal from a region whose light has not had time to reach us, because the signal does not yet exist at our location. The question of what lies beyond the observable universe is therefore not a question that observation can currently answer, and the honest position is to name what physics implies, what theory suggests, and where both run out. What physics implies begins with a problem that the standard Big Bang model, without modification, cannot solve. The cosmic microwave background arrives at 2.725 Kelvin from every direction in the sky, varying by only 1 part in 100,000 across the full sphere. This uniformity is, on careful examination, deeply puzzling. 2 points on opposite sides of the observable universe, separated by approximately 93 billion light-years, have never been in causal contact. No signal traveling at the speed of light since the Big Bang could have crossed from one to the other, because the observable universe is larger than light could have traversed in its lifetime. Yet these causally disconnected regions are at the same temperature to extraordinary precision. In ordinary thermodynamics, regions reach the same temperature by exchanging energy, by being in contact long enough for their temperatures to equilibrate. Regions that have never been in contact have no mechanism for equilibration and no reason to share a temperature. The CMB's uniformity implies that the regions we observe on opposite sides of the sky were once in thermal contact, that they share a common temperature because they were once part of a region small enough and dense enough that equilibration had time to occur. In the standard Big Bang model, expanding from a hot, dense state at a rate governed by the matter and radiation it contains, this does not happen. The regions visible on opposite sides of the CMB sky were already causally disconnected at the moment of last scattering, already separated by more distance than light had crossed since the beginning. Their temperature uniformity has no explanation within the standard framework. The flatness problem is related and similarly precise. The universe's spatial geometry, whether it curves like a sphere, like a saddle, or lies flat, is determined by its total energy density relative to a critical value. A density above critical produces positive curvature. Below critical produces negative curvature. Exactly at critical produces spatial flatness. The Planck satellite's measurements indicate that the universe is spatially flat to within the measurement precision of roughly 0.5%. Spatial flatness is not in itself puzzling. What is puzzling is that flatness in the Friedmann equations is an unstable equilibrium, a universe that begins slightly above critical density will curve increasingly positively as it evolves, eventually recollapsing. A universe that begins slightly below critical density will curve increasingly negatively, expanding forever into a cold, sparse state. For the universe to be as flat as it is today, 13.787 billion years into its evolution, the density at very early times must have been extraordinarily close to the critical value, within 1 part in 1060 at the Planck epoch, the earliest moment at which the known physics applies. This is not impossible, but it requires the initial conditions to be fine-tuned to a degree that calls for explanation. Alan Guth was a particle physicist at Stanford, working through the late 1970s on problems at the intersection of particle physics and cosmology, the behavior of matter at the energies that existed in the very early universe, where the temperatures were high enough that the fundamental forces of nature were unified in ways they are not at lower energies. On the evening of December 6, 1979, working through the implications of a particular theoretical mechanism involving a field associated with the unification of forces, Guth recognized that if the early universe had passed through a brief phase in which that field was stuck in a high-energy configuration, a false vacuum, in the vocabulary of quantum field theory, the universe would have expanded exponentially during that phase, doubling in size on an extraordinarily short timescale, continuing to double until the field decayed into its true minimum and the exponential expansion ended. In his notebook, Guth wrote the words "spectacular realization" and underlined them twice, then worked through the night calculating the implications. The implications were that both the horizon problem and the flatness problem dissolved. Exponential expansion from a region small enough to have been in causal contact, a region that had time to reach thermal equilibrium before inflation began, would stretch that equilibrated region to a size far larger than the observable universe, making the uniformity of the CMB a natural consequence of inflation, rather than a coincidence requiring explanation. Curvature, similarly, would be stretched away by the exponential expansion. Any initial curvature, positive or negative, would be diluted to values indistinguishable from zero by the enormous growth in scale, just as the apparent curvature of Earth's surface becomes negligible at scales much smaller than the planet. A universe that emerged from inflation would be spatially flat regardless of its initial curvature, to a precision far exceeding what any measurement could detect. Guth's inflationary period lasted an extraordinarily brief time, from approximately 10^36 seconds to 10^32 seconds after the Big Bang, a duration of perhaps 10^32 seconds, during which the universe expanded by a factor of at least 10^26. The numbers are difficult to hold in any normal sense. 10 to the power of -36 seconds is not a small number in the way that a millisecond is small. It is a number so far below any timescale that has physical meaning for human experience that the comparison produces no useful intuition. What the expansion factor implies is more tractable. The region that became the entire observable universe, 46.5 billion light-years in radius today, was, before inflation, smaller than a proton. It was small enough before that expansion that causal contact across its full extent was not merely possible but inevitable. Everything in the observable universe shares a common temperature because everything in the observable universe was once in the same extraordinarily tiny region, long enough for equilibrium to be established before the expansion began. Guth published the inflationary model in Physical Review Letters in 1981. The paper was received as a significant theoretical development. It solved the horizon and flatness problems cleanly, and it made additional predictions that could in principle be tested. But Guth's original model had a technical problem. The mechanism by which inflation ended, the decay of the false vacuum into the true vacuum, produced an inhomogeneous universe with large regions of unrehabilitated false vacuum that would create unacceptable concentrations of energy inconsistent with the observed universe. Andrei Linda, a Soviet physicist working first in Moscow and later at Stanford, solved this problem in 1982 with what he called new inflation, in which the field driving inflation rolls slowly toward its minimum rather than tunneling abruptly, ending smoothly and producing a universe consistent with observations. Lindy extended this in 1983 into chaotic inflation, a framework in which inflation begins from a wide range of initial field configurations, does not require the fine-tuned initial conditions that earlier models needed, and continues in different regions at different times. Chaotic inflation's most significant implication for the question of the universe's extent is the concept of eternal inflation. In Linda's framework, quantum fluctuations in the inflating field constantly push some regions back into inflationary expansion, even as other regions complete their inflation and transition to the ordinary matter and radiation-dominated expansion of the standard Big Bang. The result is a universe in which inflation never completely ends, in which the inflating volume is always larger than the volume that has stopped inflating, because exponential growth continually outpaces the fraction of volume that decays into the standard post-inflationary state. Each region that stops inflating produces what might be called a pocket universe, a bubble of post-inflationary space-time embedded in the larger inflating background, expanding and cooling from its own hot, dense beginning. The observable universe is, in this framework, one such pocket, a region of post-inflationary spacetime that has been expanding for 13.787 billion years, surrounded by an inflating background that extends indefinitely in all directions and in which other pockets are constantly forming. The multiverse that eternal inflation implies is a theoretical framework rather than an established result. Its predictions are, in most formulations, difficult or impossible to test directly. Other pocket universes are causally disconnected from ours, separated by the inflating background through which no signal can travel. Some physicists regard this untestability as disqualifying. A framework that cannot be tested is not physics in the relevant sense, regardless of how elegantly it resolves the problems it was constructed to address. Others argue that the framework's internal consistency, its resolution of fine-tuning problems, and its derivation from well-motivated particle physics models give it substantial credibility even in the absence of direct tests. The debate is genuine and unresolved, which is the correct characterization of the field's current state. What can be said with more confidence is the implication of inflation, even in its most conservative formulations, without eternal inflation, for the ratio of the total universe to the observable one. The minimum expansion factor during inflation, in the simplest models that solve the horizon and flatness problems, is approximately 10 Cia 26. This means the total volume that originated from the same pre-inflationary region as the observable universe is at least 1078 times the volume of the observable universe, a number that exceeds the number of atoms in the observable universe by many orders of magnitude. The total universe in these models is not merely larger than the observable universe. It is larger by a factor so extreme that the observable universe, with its 2 trillion galaxies, its 1024 stars, its 46.5 billion light-year radius, is a negligible fraction of the whole, smaller relative to the total than a single atom is relative to the observable universe itself. The observational signatures of inflation that can in principle be tested lie in the CMB. Inflation predicts a specific spectrum of primordial gravitational waves, ripples in spacetime produced during the inflationary expansion, that would leave a distinctive imprint on the polarization of the CMB, a pattern called B-mode polarization. The amplitude of this signal depends on the energy scale of inflation, which varies across inflationary models. But several favored models predict a signal detectable by sufficiently sensitive CMB polarization experiments. The BICEP-2 experiment announced a detection of B-mode polarization in 2014 that was interpreted initially as a gravitational wave signal from inflation, but subsequent analysis showed that the signal was consistent with polarized dust emission from the Milky Way rather than primordial gravitational waves. The search continues with newer instruments, the BICEP array, the South Pole Telescope, and eventually the proposed CMB-S4 experiment, though no confirmed detection of inflationary gravitational waves has been made. Beyond the horizon, then, the physics says more. More space of the same kind as the observable universe, extending in all directions past any boundary measurement can reach, containing matter and radiation organized by the same laws that govern the observable volume, in concentrations and distributions that cannot be directly examined. Whether that extension is finite or infinite, whether the regions beyond our horizon share the same physical constants and the same particle physics that our observable universe exhibits, whether the concept of the multiverse has physical meaning or constitutes a philosophical position rather than a scientific one, these questions sit at the boundary between what current physics can address and what it cannot. The boundary is real. The questions on the other side of it are real as well. And the honest scientific posture is to hold them open without performing either their mystery or their resolution. Chapter 12. What Universe Means. Robert Williams had been director of the Space Telescope Science Institute for 3 years when he decided to point the Hubble Space Telescope at nothing. The field he selected was a small region near the handle of the Big Dipper, chosen specifically because it contained no bright stars, no known galaxies, no objects of particular interest in any catalog then available. It was, by every existing measure, an empty patch of sky. The field subtended about 5.3 square arc minutes, roughly 1/24 millionth of the total celestial sphere. Williams used his director's discretionary time, an allocation given to the Institute's director, to spend on observations of his own choosing, independent of the normal peer review proposal process, to observe this empty field for 10 consecutive days in December 1995, accumulating 150 orbits of exposure time across 342 separate images in 4 wavelength bands. The decision was not without opposition. Director's discretionary time is a limited resource, and spending it on a field containing nothing visible was, to some colleagues, difficult to justify. Williams's argument was straightforward. If galaxies were distributed roughly uniformly across the sky, a sufficiently deep image of any sufficiently dark field should reveal them. The field was not empty, only apparently empty, and the depth required to reveal what was actually there had not previously been achieved. The images were taken, combined into a single deep mosaic, and released publicly on January 15, 1996. The mosaic contained approximately 3,000 galaxies. They were present at every depth the image reached, distributed across the field in every morphological type: spirals, ellipticals, irregulars, merging systems, compact blue objects whose classification was uncertain, at redshifts ranging from nearby to cosmological distances, approaching the edge of what the camera's sensitivity could reach. The field that contained nothing contained thousands of galaxies, and the implication was immediate. Every comparable patch of sky, whether it appeared empty or not, contained a comparable number. The sky was not sparsely populated at depth. It was filled at every point with galaxies stacked behind galaxies to the limits of the instrument. The Hubble Deep Field became one of the most reproduced astronomical images in history, not because it showed anything individually spectacular. No single galaxy in the image is particularly famous. No dramatic collision or explosion dominates the frame, but because of what the image as a whole implied about the scale of what existed beyond the visible. Subsequent programs extended the depth and wavelength coverage. The Hubble Deep Field South in 1998, observing a comparable field in the southern sky. The Hubble Ultra Deep Field in 2004, reaching to redshifts of around 6 or 7, observing galaxies as they existed when the universe was less than a billion years old. The Extreme Deep Field in 2012, combining 10 years of observations of the ultra-deep field central region into an image reaching galaxies at redshifts approaching 10. Each deeper image found galaxies where shallower images had found none, extending the populated sky further back in cosmic time. The James Webb Space Telescope's first deep field, released on July 11, 2022, covered a patch of sky equivalent to a grain of sand held at arm's length. Within that grain of sand, that imperceptible sliver of the full celestial sphere, JWST resolved thousands of galaxies, many of them at redshifts exceeding 10. Observed as they existed when the universe was less than 500 million years old. The galaxies in the JWST deep fields are not faint smudges, but resolved objects with visible structure, disks, clumps, arcs from gravitational lensing, at distances so large that the light now arriving left before any of the stars in the Milky Way that are currently visible to the naked eye had formed. The image is not a picture of the distant universe as it exists now. It is a picture of the distant universe as it existed then, the light carrying a record of conditions so early that the cosmic web was still assembling its first large structures. The 2 trillion galaxies that Christopher Consoli's 2016 analysis implied within the observable universe distribute across that volume in a way that the deep fields make viscerally concrete. The observable universe contains, within its 46.5 billion light-year radius, a number of galaxies that exceeds the number of grains of sand on all of Earth's beaches by a substantial factor. Each galaxy contains, on average, somewhere between tens of billions and a few trillion stars. Each star may have planets. The numbers accumulate past any useful comparison, long broken before they reach their final value, which is why the deep fields matter as images, not because they quantify the population, which the Consoli's analysis does more rigorously, but because they make the populated sky a visible thing rather than an abstract one. Every point in the sky, down to the scale of a grain of sand held at arm's length, contains thousands of galaxies if the telescope is sensitive enough to find them. The sky is not the background, the sky is the content. Against this content, the question the episode's title asks, how big is the universe compared to our galaxy, has a series of answers depending on what is meant by the universe. The Milky Way is approximately 105,700 light-years in diameter. The local group containing the Milky Way, Andromeda, and roughly 52 smaller galaxies spans approximately 10 million light-years. Laniakea, the supercluster of which the local group is a peripheral member, stretches roughly 520 million light-years across. The observable universe extends 46.5 billion light-years in radius, a diameter of 93 billion light-years. Compared to the Milky Way, the observable universe is approximately 880,000 times larger in linear scale, and the volume ratio is the cube of that, something on the order of 7 × 10^17, a number with no natural comparison. And this is before the question of what lies beyond the observable universe is introduced, at which point the ratios lose their last foothold in anything that can be held in mind. The word universe carries two meanings in current usage, and the distinction between them matters more than it is usually given credit for. In ordinary language, universe means everything that exists, the totality of space, time, matter, and energy without boundary or remainder. In observational cosmology, universe often means the observable universe, the sphere of 46.5 billion light-years centered on our location, the portion of everything from which information has reached us. These two uses are not always distinguished, and the distinction matters because they may refer to things that differ enormously in extent. The observable universe is a subset of the whole, bounded not by a physical edge but by a limit of information. Whether the whole is finite or infinite, spatially closed or open, singular or multiply instantiated, these are questions that the observable universe's data constrains but does not determine. General relativity describes the universe's large-scale geometry through the Friedmann equations, which admit several possible spatial topologies. A spatially flat universe, consistent with what the Planck CMB data indicates, could be infinite in extent, filling all of space with matter and radiation at roughly the average cosmic density, extending without boundary in every direction. Or it could be finite but without boundary, curving back on itself through a topology analogous to a three-dimensional torus, a shape that would eventually return a traveler to their starting point without ever encountering an edge. The Planck data does not distinguish between these possibilities. Flatness rules out a small closed universe that would produce detectable correlations in the CMB pattern. The universe is not so small that its topology wraps within the observable volume, but it permits a flat universe of any size, from slightly larger than the observable to infinite. Inflation pushes toward the larger end of this range. If inflation occurred, and the evidence from the CMB's flatness, its uniformity, and the specific spectrum of its fluctuations is consistent with inflationary predictions, even if no smoking gun signature has been confirmed, then the total universe is many orders of magnitude larger than the observable portion. The minimum estimates, as described in the previous chapter, place the total volume at 1078 times the volume of the observable, and in models of eternal inflation, the total is either arbitrarily large or genuinely infinite, depending on formulation. The observable universe, against this backdrop, is not a significant fraction of the whole. It is a sample, a specific and informative sample, but a sample. What this means for the question of the universe's size relative to the galaxy is that the question is nested inside a larger question about what boundary is being drawn. The observable universe is 880,000 times larger than the Milky Way in linear scale, and this ratio is established by measurement, Cepheid variables, rotation curves, the CMB geometry, the Hubble constant. The total universe is larger than the observable by a factor that theory estimates, and observation cannot currently constrain below several orders of magnitude. And the Milky Way, 1,5,700 light-years across, is one of perhaps 2 trillion galaxies within the observable portion alone, a structure that is, within the full context of what the measurements imply, neither large nor small but simply local. It is the galaxy that happens to contain the instruments that made all the measurements, which is the only sense in which it is central to any of this. The deep fields make a related point more quietly. When Williams pointed Hubble at an empty patch of sky and found 3,000 galaxies, he was not discovering that the universe was full. That was already implied by the statistical analyses of galaxy surveys. He was demonstrating it in a form that required no statistical argument, no theoretical framework, no prior knowledge of cosmology to absorb. The emptiness was apparent. The galaxies were real. The sky that looks dark between the visible stars is not dark in the sense of empty. It is dark in the sense that human eyes are not sensitive enough, and exposures of a few seconds are not long enough to register what is there. Given 10 days in a telescope in orbit, the darkness fills. That filling continues beyond the deep fields, beyond the JWST images, beyond the most distant object yet detected at any wavelength. The recombination surface, the last scattering surface from which the CMB photons departed, sits at a redshift of approximately 1,100, far beyond the most distant galaxies resolved in the deep fields. And beyond it lies the opaque plasma of the early universe, inaccessible to photons and therefore invisible by definition to any optical or radio instrument. Gravitational waves from the inflationary epoch, if they exist at detectable amplitudes, would carry information from earlier still, from the first fraction of a second, before the universe was transparent to anything. The instruments to detect them at cosmological amplitudes do not yet exist. The information is, in principle, there. Beyond all of this, beyond the last scattering surface, beyond the particle horizon, beyond the reach of gravitational wave detectors not yet built, the universe continues in whatever form it takes at scales that no measurement has reached. The CMB cools by fractions of a degree across timescales that dwarf the current age of the universe. Light moves through the voids between galaxy filaments, crossing distances that will take billions of years to cross, carrying information about the galaxies that emitted it toward detectors that may or may not exist when it arrives. The large-scale structure shifts slowly under the competing influences of gravity and dark energy, filaments thinning as accelerating expansion stretches the distances between clusters, voids growing as the matter at their boundaries is drawn outward into the surrounding web. These processes do not require observation to proceed. They were underway before the first instrument was built to measure them, and will continue after the last one ceases to function. The universe does not have a size in the way that a room has a size, with walls that can be measured and a volume that can be calculated and reported as a single number. It has a measurable portion, the observable universe, 93 billion light-years across, containing 2 trillion galaxies and 1024 stars, and everything that human instruments have ever detected or will detect. And it has an extent beyond that portion which physics describes, in terms of probabilities and theoretical frameworks and minimum estimates derived from the geometry of inflation. The Milky Way, 105,700 light-years across, sits within the measurable portion as a single structure among 2 trillion, its size dwarfed by the observable universe by a factor that arithmetic can produce, but intuition cannot process. And the observable universe sits within the whole as a region whose relationship to the total is constrained by theory to be negligible, a small, specific, informationally rich patch of something that extends, in all likelihood, vastly further than any signal has yet traveled to tell us. The light keeps moving. The expansion continues. The background radiation, now at 2.725 Kelvin, will be at 2.724 Kelvin in a few billion years, and cooler still after that, the photons losing energy to the expanding space through which they travel, carrying their record of the early universe across distances that grow as they cross them. Somewhere in the voids between the filaments of the cosmic web, light emitted by a galaxy a billion years ago is still traveling through space that contains almost nothing, on its way to a location that may or may not have a detector waiting. The process is indifferent to whether it is observed. It proceeds at the speed of light, which is the only speed it knows, through a universe whose extent it will never fully cross. The journey is complete. Rest well.